Good morning, everybody. Who's tired? Anyone? But we have such a great day ahead of us. It's day 3, the third and final session of the Astronaut Scholar Technical Conference, and it's been amazing to see everyone's presentations yesterday, and I look forward to them today. To help guide us through the session, we have our rock stars over here, Ashley Monahan, 2018 Astronaut Scholar, and Carol Fitzgerald Tyler, dedicated ASF trustee, mentor, longtime supporter, and what I didn't know, she's also a comedian. So we're going to do things a little bit different, and you have a special treat. We're going to kick this off with our 2025 Neil Armstrong Award of Excellence honoree, Miss Jessica Blomberg. If you could come to the stage. Let's give her a round of applause. She's a 1996 and 1997 astronaut scholar from the University of Central Florida. Let's give her a round of applause.
Well, good morning, everybody. My name is Jessica Blomberg. I'm the founder and CEO of Quality CMC Consulting. I'm also an astronaut scholar from 96 through 98. Today, we'll be talking about CMC. It's the science that makes medicine work. We'll be going over a short overview of what CMC means and then a few general case studies. So first, welcome to the world of CMC, where acronyms will be your best friend. The first acronym we'll go over is what CMC means, and that's chemistry, manufacturing, and controls. And so that's really how a drug or device is made. These are some different types of drug products I've worked on in my career. And what we're really looking after is what is that active ingredient in your drug substance, how to formulate into your drug product, what tests you want, that acceptance criteria, and how to store it and for how long. Think about the labels you have on the drugs in your cabinet. All of this goes into a regulatory filing. So this is the triangle. It's called the Common Technical Document for the United States. And there's different aspects for clinical tox and CMC, with CMC in the left corner, and there's 55 sections alone in the CMC section for the filing. But when you put together a filing, there's a lot of other disciplines that go into that, right? It's the safety from your tox, it's your clinical plan. And so when you're putting together your IND, it's a little bit like herding cats. So for CMC, it's called another acronym. It's called CGMP, so Current Good Manufacturing Practices. And this is dictated by the law for the Code of Federal Regulations. The FDA helps to regulate that. And so they've been around for about 120 years. And over the course of the years, they're really focusing on patient safety. And what they look for CMC is called CISPQ. So that's going to be your safety, identity, strength, purity, and quality. A lot of questions I get asked sometimes is, when do my GMPs kick into my process? And so you can have a lot of different starting materials for your manufacturing process. You have small molecules, which are typically your reagents. But for biologics, you have really complicated starting materials. So microbial, mammalian cell lines, you can even have human cells. And so it's really important to know when your GMPs kick in legally. So for your typical drug product development phases, that's one positive thing out of COVID, is that it got the public more aware of what clinical trials mean. But typically you'll start on your tox, your pre-IND enabling studies. You go into your phase 1, your phase 2, which are efficacies, and your phase 3. During the whole time you add more people, you're scaling up your manufacturing process to your batch size and learning more about your manufacturing process and your test methods. This will take years and a lot of money. And so it's really important to be phase appropriate, so you don't want to put commercial requirements on when you're trying to get first-in-human studies done. So we have in the United States the FDA, but in other countries they have their own regulatory bodies. And so it's really important when you're developing your clinical trial strategy to have those countries identified. And these are just a few of the countries, the different regulatory bodies. I'm sorry, I get a little nervous, so my voice gets a little jumpy. So, so for your drug substance manufacturing, your crash course, on your left is for a typical process for a small molecule. Your right is a biologic specific for a monoclonal antibody. These different steps represent unit operations. So you have different inputs and outputs. And as you go through your clinical development, your other stages, you scale up, you learn more about your process and your test methods. The drug product, right? So you take that active, you do your excipient compatibility studies, you figure what product type the clinical team needs. And so there's various forms that you have, and you go through the same ropes that you do for the drug substance. As you scale up, you know more about your process, you know more about your test methods, and so that when you have your market application, you have a robust quality product. Often the stepchild a little bit of CGMPs is the label, storage and distribution. So everyone notices it has like how you can store your drug and for how long. So that's the studies that get done for there. Uh-oh. Oh no. Something happened on the screen. All right. So now that we've all had a crash course on what the manufacturing part of CMC means, now we'll go into the controls, which is the testing. And so on a one page, we'll go over that. And that is your item specification. And so this is kind of your list of tests based upon the attribute that you need that the USP and your Farm Europe will require. You have the method, and so that method will change as you go through your development, and then the acceptance criteria. You can do testing at the different unit operation boxes I showed, so that can be your in-process monitoring or in-process control, but typically also you do it at the end, right? You do it at the drug substance and drug product, and then you figure out your temperature and how long you can store it for. As you go through your development, so your phase 1 to phase 3, your acceptance criteria will tighten. So early on, you might have like a purity of 85%, but when you get to your market application, that might be more like 90, 95. So now that you all have the power of understanding what CMC means, and this is He-Man, in case folks don't know, thought about that. I'm like, maybe. We're gonna go over a couple of case studies, 3 in exact, and please keep in mind with my job type, I have to stick to non-confidential information when it's out in the public domain, so just bear that in mind. The first case study is for bringing a therapy for chronic regional pain syndrome to the United States. So CRPS is what it says. It's a chronic pain disorder. It usually happens after a bone injury or surgery. And you can see here the joints get very red, swollen, and the pain can last for months or years. And so this is actually an image here of what it looks like. The top picture is actually my foot. I had this condition after leg surgery in 2019, so when this project came across my desk, I was really excited to bring a therapy to the United States for when I had the disease. There was nothing to help me. To the left is a pain scale of how bad CRPS is. It's right underneath kidney stones, and somehow they put delivering a baby below a kidney stone. I don't know if that's true, but I can contest that CRPS is more painful than childbirth. I only had one instance more painful than CRPS, and that was a car accident in 2022 where I broke and displaced 8 ribs and fractured my spine. But second to that, it's the CRPS. So I was really fortunate. I'm really excited to bring this to the United States. So we're bringing it over from Italy, putting it into vials and get ready for our phase 3 trial. Now the second case study is designing a novel control strategy. And so this is for a VLP vaccine, so a virus-like particle. The particle probably looks like COVID, and it's designed to look like a virus. This technology actually was a spin-out from David Baker's Institute for Protein Design Lab, and he won the Nobel Prize last year. So at first, we were looking at a monovalent vaccine, so just for one of these respiratory diseases. Later in clinical development, we went and did a bivalent vaccine, but we were global, right? And so it was really intricate to try to get a vaccine strategy that would be accepted by all regulatory bodies. And for me, it was a lot of fun because there was a lot of components to putting this together. So you can see in one of the molecules, or the VLPs, you have these chicken legs and this inner core. Each of those are different components. One's made in a mammalian cell line, the other in a microbial. We purify those, but when we combine them, they spontaneously will form this VLP. So it's quite exciting. So we had multiple intermediates, a couple of drug substance, and a drug product. So figuring out what to test when was a lot of fun. This was acquired by AstraZeneca last year for $1.1 billion, so a success story. Case study number 3, this is for a gene therapy product. So trying to bring that from the lab to the clinic. This one client in particular in California, they have an AAV that crosses the blood-brain barrier naturally through an intravenous injection. So one injection goes into the brain, stays there, and hopefully it will be cured. The cell and gene therapy space is quite evolving within the FDA, so it feels like almost every week now they come up with a new guidance document that you have to abide by. But the client did their own in-house manufacturing in most of their testing. So when I came on, I was helping their R&D team transition from research and development to what GMPs. So what does that mean for running a quality control lab? How do you develop those methods? And what are those acceptance criteria? I also helped author their IND sections, including their elucidation and structure. And for this program, we had over 30 methods. So we heard from some of the talks about maybe one, so multiply that by a lot. These 2 INDs got approved this year, rare diseases, CNS, with one in particular for a certain type of Parkinson's with a gene disorder. And so I'm really excited to see those go into the clinic pretty soon. So I want to thank you all today, and I hope you enjoy the world of CMC.
Fantastic. Do we have a couple of questions for Jessica?
Yes, sir.
So you, thank you, this was a great presentation. You talked about the phases 1, 2, 3 that you go to drug approval. Did you ever go back in your phases? You discover something in phase 2, did you go back to phase 1, or it goes through these?
Maybe if you're changing more the drug product type, and so then you might go into doing an earlier phase. But actually, if you have, say, an asset that's out of phase 3 and you're doing a phase 1, the FDA does have more expectations of where that will be at. You're welcome.
How about another question for this fantastic research and presentation?
Yes?
Wake up.
Got it. I'm very curious. I have a veteran friend who has the complex regional from a deployment injury. Is there interest in, is the VA interested in the therapeutic for veterans? I'm just curious long term.
I would expect it. I mean, so once this does get approved, it would be free for any physician to write that script. Yeah. But I really am glad that maybe a therapy could help your friend that was coming over.
One more question for Jessica.
What determines how long you can store the drug and use it?
Sure. That's usually dictated, well, there's a couple, the majority is your impurity profile, right? So if your bottle says store in the refrigerator and it's good for a year, please don't keep it in your car and use it on year 3 because we did not study those effects. But that's really, what, how you work that.
Wow, thank you, Jessica, so much. We're so excited that you're our award recipient. See me later about that chronic pain business, would you please? Good morning. Good morning. Oh, come on, do better than that. Good morning. Good morning. I love it. Good morning, everybody. Welcome again to session 3 of our technical conference. My name's Carol Fitzgerald Tyler. I'm delighted to be your host with my wonderful co-host Ashley over there. Couple of public service announcements really quick. Number 1, we will take a break. Don't worry about your coffee intake. Number 2, Ashley and I are very keen to hear all of your questions. So when you do ask a question, please wait for the microphone so that all of us can hear it. So we're super excited. Yesterday was an awesome day with our scholars. We're going to have another awesome day today. So welcome. enjoy the presentations, and we will be starting right now with Maggie Campbell. Maggie, come on up. She's going to talk to us about being slammed into action. Way to start the morning.
Good morning. My name is Maggie Campbell, and I am a senior at Virginia Tech studying ocean engineering. And today I will be presenting my research, Slammed into Action, assessing the impact of wave interactions on high-speed planing vessels and their safety implications. So, why are we doing this research? I would like you all to imagine that you are a Navy SEAL, or James Bond. You have to get from point A to point B using a high-speed boat in a certain amount of time. So you're going at, say, 45 knots, and you hit a wave field. Now, a few things can happen. One, you have to slow down, meaning you don't reach point B on time. Two, you slam into the wave so hard that your boat breaks, and you're really not reaching point B. Or, option three, you slam into a wave and your body slams forward into the console or into the steering wheel, and you break. Also not good. All of these cases are going to result in mission failure. So the goal of my research is to study the interaction between these waves and these boats so that we can minimize these effects and make the boats safer for their operators. So for you landlubbers out in the audience, I'm going to start out by explaining some nautical terminology using the Brigantine Matthew Turner, which is actually a boat that I worked on last summer. So we have the front of our boat, which is called the bow, the back of our boat, which is called the stern, the middle of the boat is creatively called midships, and then something that's really going to come up a lot in this presentation, which is the body of the boat, or the hull. You're going to want to remember that one. So now we're going to get into the research. So this is a video that is courtesy of the U.S. Naval Academy that was taken by my PI, Dr. Christine Gilbert, when she was doing research there. And this is a model that is interacting with a wave field generated by a wave maker. Now, this is the goal, but one of the challenges that we have at Virginia Tech is that we don't actually have a wave maker. So we had to get a little bit creative. So what we do is we actually rotate our frame of reference. We have our water, which is usually at an angle, and our boat, which is flat, and we're actually going to rotate that. So now our water is our horizontal, and our boat is coming in at an angle. This keeps the impact location constant, so whatever we find out is applicable to both situations. And for this, we use a model called a generic prismatic planing hull, or GPPH, which you can see some diagrams of here. So you're going to see here an example of a slam. That's what it looks like. So what are we actually looking for when we're doing these slams? Well, in previous studies, we've worked on looking at the overall force on the hull. For that, we use force sensors. And we've looked at the pressure along the hull, where we're actually using more localized pressure sensors. But the goal of my research is to figure out more about that pressure using imaging. How are we going to figure out pressure using imaging? Well, we're looking at something called the spray root. The spray root is defined as the point of maximum curvature of the water surface when it meets the boat. We can simplify a boat's hull by using a wedge. And when a wedge enters the water, it's going to displace some of that water, and the displaced water has to go somewhere. So it's going to kind of squirt out the sides. Everyone's dropped a rock into a pond before. So when that water folds over as it squirts out the side, the very, very base of that fold is the spray root, and that's what we're looking for. Why is the spray root important? Well, there's a correlation between the spray root propagation and the location of peak pressure distribution along the hull. So if we can track the spray root, we can track where that peak pressure is. And how do we do this using imaging? Well, we're going to first have to collect that data. And to do that, we're going to use a model mirror camera system. So our model is going to descend into the water at a specified location over top of a mirror, which is located on a frame at the bottom of the pool, as you can see in the center image. And then that mirror is going to reflect our image 90 degrees to the right through a window, which you can see in this bottom right image, to a camera, which is located down in a pit beneath the floor. So then we're going to be able to take the high-speed images from that camera and use them in a contrast-based image processing MATLAB code to actually track that spray route. And you're going to see some preliminary results here. This is actually the model moving across the mirror, and you can see it's beginning to enter the water, and that shadow right there is the spray route. And that's what we're going to be trying to track. In the future, what we're going to want to do is we're going to want to increase our mirror size, get a better lighting setup, and increase our camera calibration and image processing tools so that we can get some better information on where that spray route actually is. So I would like to acknowledge my PI, Dr. Christine Gilbert, and PhD candidate in the lab, Ben Darden, without whom I would never know how to operate the tow tank, as well as the Office of Naval Research for sponsoring this project, and the Astronaut Scholarship Foundation for allowing me to present it here to you all. Thank you. Are there any questions?
Thank you, Maggie. I'm not sure about getting on a cruise ship anytime soon. Who has a question for Maggie? In the front row.
So how much does the experimental results vary from what you would actually see in the ocean, where your waves might be coming from slightly different angles? And can you still predict based off of the model, okay, we know this is where the maximum pressure is. Is that also expected with what you would see in the ocean in more chaotic situations?
That's actually one of the big challenges of studying wave-boat interactions, is because the wave fields that you see on the ocean, there's such a variety of factors that are influencing them that we actually really only model them using statistics, because any given wave field is going to be non-repeatable. And so that's the reason why we're studying a very, very small portion of just the impact, because then that data is going to be transferable to real life situations, because it's we're not studying repeated impacts or how it's interacting between waves when it's in the trough. We're just studying that impact moment in this portion of the research. And so it is applicable to those real life situations because it's such a small portion of it.
Great. Thank you so much, Maggie. Next, we would like to welcome Nathan Wagner, and he's going to talk to us about benchmarking. Welcome, Nathan.
Hello, everyone. My name is Nathan Wagner. I'm a rising senior at the University of Wisconsin-Madison, and I'm excited to present my research on quantum computing. My project's name is called Benchmarking a Neutral Atom Quantum Computer. So, analogously to how classical computers use bits to store information, quantum computers use what's called qubits. But one of the major challenges in quantum information science is figuring out what exactly those qubits should be. Some people are experimenting with trapped ions. Some people are experimenting with superconductors. What our group does, yesterday there's a presentation by Britain about atomic clocks. So our group uses a lot of the same technology in our quantum computers. They're called neutral atom quantum computers, and we use the 2 clock states of cesium to encode our quantum information. So why do we do this? Why neutral atom quantum computing? One of the reasons is due to what's called all-to-all connectivity. On certain quantum computers, if you think about the qubits of being on a grid, you can only entangle nearby qubits, like a king's move away. Entanglement is a very important operation in quantum computing, and it's one of the hardest to implement. So what we're able to do on a neutral atom quantum computer, based on how our entanglement works, is we're able to connect any 2 qubits in our grid basically in one gate. So my work aims to determine how much that actually improves the performance of our computer. So my work comes in 2 different stages, one of which is developing a noise model that's able to accurately predict experimental results on a computer. So a lot of that was done using experimental data that was published in Nature prior to the project. And just creating a noise model like this really helps with determining quickly, if you have an idea for an experiment you'd like to run on this computer, whether or not it's even worthwhile to do, how noisy the result will be. So this is something that I used in my work. So so I applied this in basically determining how our computer would perform under a benchmark, specifically an application-oriented benchmark. This is in contrast to some randomized benchmarks that are used, such as quantum volume. In those benchmarks, you simulate a series of random 2-qubit gates, whereas in our benchmark, we're given a list of a few different circuits that are important in quantum information science. Some example of those are a quantum Fourier transform and a phase estimation circuit. And if you've heard of the famous Shor's algorithm, that's basically a beefed up phase estimation circuit. So we've been given a lot of different circuits in this benchmark, so we got a lot of really good results. We found that in a specific category of circuits called the subroutine circuits that include phase estimation, quantum Fourier transform, we're able to get an improvement of 10 to 15% by comparing an all-to-all computer with a nearest neighbor computer. So this really helps with motivating our future research, in that we'd like to explore some of these circuits that fit into the subroutine category more, because it's the ones that shown the most improvement. It's the ones that seem to be the best to run under our computer. And we'd also like to explore some benchmarks that focus more on these subroutine circuits, or mid-width circuits. So I'd like to thank my professor, Professor Safman, everyone in the Safman group, and I'd like to thank the Astronaut Scholarship Foundation for bringing us down this weekend, allowing me to present my research, and all the support they've given me.
Thank you, Nathan. Who has a question for Nathan?
Hey, Nathan. Thank you for the fascinating presentation. The 10 to 15% figure is quite striking. So my question for you is, how does the fidelity of performing, say, like a CNOT gate between two long-range sites compared to the fidelity of performing a CNOT between, for example, like nearest neighbor sites?
Yeah, so the fidelity, so in a lot of these shorter circuits, the fidelity did not change much, or a lot of these shorter interactions. We're able to tailor, we have different Rydberg interaction strengths between qubits at different sites, so we're able to tailor CZ gates to accommodate those. But in general, the fidelity does decrease, and that's more apparent as you get into circuits with higher amounts of qubits.
Got it. Thank you. Impressive work.
Thank you.
Thank you. Who has another question for Nathan?
Hey, Nathan, great talk. I wanted to ask, if you developed the benchmarking strategy you used here, how did you verify it? How do you know that the numbers you're getting are actually representative of computer performance?
Yeah, so the benchmarking suite that we developed was published earlier. It's a series of a bunch of, so it was published by Lewinsky. And I guess we were able to verify that by, a lot of it was due to our, the noise model that we used. So in developing that, we were able to get a good fit with experimental data. We were able to reproduce some of the other experimental results in our previous work.
Wonderful. Thank you so much, Nathan. So, speaking of quantum entanglements at 9:35 in the morning, let us now welcome David Balut, and he's going to tell us about more quantum entanglements. Welcome, David.
Yeah, thank you for the introduction. Before I begin, I'd like to thank my advisors and collaborators on this project, Professors Peter Abamonte and Barry Braidlin at the University of Illinois. as well as the Astronaut Scholarship Foundation for giving me this opportunity to present my research. So thank you for that. Okay, so why do we care about quantum geometry and what I'll discuss later, quantum entanglement? So there's a major unsolved problem in modern physics, and that's how do we deal with strong interactions, or what we call strongly correlated matter. So this is what happens when you have a many particle system, and its constituents, say it could be electrons in a conductor, they interact very strongly with each other. As you can imagine, anyone that does numerics in this room can imagine that that's a very difficult computational challenge, and even for theoretical physicists, that's also quite difficult to even begin to write down a theory to explain our experimental observations. Some examples for this for your reference, these are what we call the fractional churn insulators, strange metals, high temperature superconductors, even black holes fit under this umbrella. So it's really a wide array of material and physical phenomena that we're trying to describe here. And what these all have in common with each other is that expectation values are not enough to describe the system. So what does this mean? So when you first learn quantum mechanics, you put a particle in a box and you say, what are my energy levels allowed in the system? And that actually gives you enough information to go ahead and describe compute any physical quantity that you care about. But these strongly correlated materials are just another example of systems in which that's not enough information. You need some other physical quantity that you're interested in to really describe what's going on. So as Nathan just nicely described, entanglement in quantum information science is a central additional physical quantity you need to know besides just your expectation values, for example, like say your energy levels or your ones and zeros in quantum information science. But the problem in strongly correlated matter is that we don't really have a good understanding of what's that additional thing we need to know. And so quantum geometry is a nice promising avenue of this additional physical quantity or physical phenomena we can know in a system that can help us describe and help us get us closer to understanding this major unsolved problem. So again, the main takeaway here should be that if we ought to understand strong interactions, maybe we can investigate quantum geometry, see if that's enough for us to solve this problem. And I should probably mention what quantum geometry is. And that is when we have many different energy levels like I talked about, say we have that particle in a box, well, how informationally different they are between each other, that's what we call quantum geometry. In more technical terms, that is how it's a geometrical landscape of the information phase space. But anyways, so let's move away from strong correlations and let's move to weak interactions, because we can actually go ahead and write stuff down and test these metrics. So we'll look at weakly interacting insulators. So this is what we call time binding models. This is where we say we have we have like an atomic lattice, it could be diamond or something, and we say we just have our s and p orbitals at each atomic site, and we're just going to consider weak interactions between each other. So we define a metric of our quantum geometry, and in this case, this is actually it looks like a variance because it's just the variance in the position of the electrons. So how much they vary between each atomic site. And so what we're in progress in showing, we're currently writing the paper, is, okay, if we have this metric k, we can show that it's directly proportional to the entanglement between different orbitals in the insulator. So what we really like to do is say if we can measure this quantity in an ionic insulator and a covalent insulator. And as we expect, covalent, we learned in Chemistry 101, covalent insulators share electrons. Ionic insulators have a donation of an electron, so we should expect more delocalization in, say, an ionic insulator. Or, excuse me, more delocalization in a covalent insulator. Okay, so we'll do the experiment. We go to a fancy synchrotron facility, shoot some X-rays at something, and then we extract this quantity called collidable prime. What's important to take away is that if you just simply integrate that data, do an integral on it, you can extract this k that we're interested in. And for more details, I'd like to refer you to another publication that talks about this process. But here's some unpublished data that if we actually do this for an ionic and a covalent insulator, we do indeed see that k is larger in the covalent case as we expect. So it's a really nice proof of principle that this really does work. Another thing I'd like to mention is that we have gone ahead, we have this data for more interesting systems. Let's go ahead and do this analysis for the strange metal I alluded to earlier. And we actually have really interesting results there on the quantum geometry and entanglement in those systems. So it really is seems to be a promising avenue for understanding a strong correlation. So I'd like to thank you for your time. I'll leave my email for any questions, and I'd be happy to take some now. Thank you.
Thank you, David. Who has a question?
Thank you very much. Thank you. This is kind of both for you, David, as well as Nathan. How did you account for superpositioning in noise levels and the benchmarking, and also in your geometry?
So in this case, noise levels are, So here it's a little bit different than Nathan's case. We actually just have, like, let's say, like a crystal of diamonds, say. And so we will get noise levels in our system. I mean, this is because it's a disordered crystal or anything. But what actually happens is the reason we care about insulators is because we have an energy gap. So any relevant noise levels, at least energetically, are much lower than the gap. But additionally, we detail this in this paper here. But you can actually just account for that. You can average out that noise level by counting it. When you're scaling your data, putting units on this, as you can see, this has units of reciprocal angstrom. When we go ahead and do this, we can average this against many different data points and sort of offset that. So we believe it's robust, and we detail this quite rigorously in this publication. But it's just taking lots of data is the answer.
Another question? One more?
Hey, thanks again for the interesting talk. My question is, what's the advantage of using the quantum weight versus another metric, say like the entanglement entropy? Since in this case, it looks like you have to measure experimentally a lot of two-point functions, which can be kind of challenging.
Yeah. So the main goal is specifically, can we measure it? Like, we can actually go and do this experiment and measure it. So the entanglement entropy of like a many-body system has been a hard thing to access experimentally. But what we're excited is about the fact that we can actually, as I showed here, we can actually relate the entanglement entropy to the quantum weight, and the quantum weight is experimentally accessible, which is why we care about it.
I see. So do you average over a large amount of quantum weights to get the whole system? Since it looks like in this equation, you just measure two sites, and then you get the Kij.
Sorry, yeah. For clarification, Kij is just the subscripts are position indices. So this just actually depends on which direction of the crystal you measure. So it just depends on, like, say, crystal symmetries, but it should be a general, like, if you go with the small q limit, so near the gamma point in K-space, then this is something that's just a general feature. So kind of like your entanglement entropy. So it's the closest we can get to entanglement entropy in an insulator, basically.
Gotcha. Thank you.
Yeah, thank you for the question.
Thank you, David.
Thanks.
Pythagoras is smiling at you right now. All right, next we want to welcome Ishan Patel to talk about spin-orbit coupling. Welcome, Ishan.
Hi, my name is Ishan Patel. I'm a student at the University of Virginia studying physics and math. And today I'd like to talk to you about my research that I conducted at Boston University over the summer. And before I begin, I'd like to acknowledge both Boston University for their great hosting of my RU program and my PI, Professor Sahar, who was invaluable throughout this process. So first, I'd like to give some motivation for why am I studying doped chiral carbon nanotubes. So just for reference, so we're on the same page, that's a carbon nanotube, and that's the one I was studying. So why are carbon nanotubes interesting? So maybe you've heard, there's like really interesting mechanical properties of carbon nanotubes. They're really strong. Yeah, I'm not interested in that. I'm interested in the electronic properties of these carbon nanotubes. And so to me, the most interesting thing about these chiral carbon nanotubes is that spin up and spin down electrons can generally have different energies in these carbon nanotubes. And that's a result of them being not having an inversion symmetry, for those of you who are interested. And so it turns out that this lack of an inversion symmetry and this energy difference of the spin up and spin down electrons can have wide applications in a field known as spintronics. And spintronics is just like electronics, where electronics uses the charge degree of freedom to store and carry information, and spintronics attempts to do the same with the spin degree of freedom of electrons. So it's a very interesting field. And the spin splitting, the energy difference between the spin up and spin down electrons of these carbon nanotubes has an application in this field, right? So motivation for studying this problem. And so the even more interesting thing is, can we tune this spin splitting, right? Is there something we can do to change its magnitude and where it occurs in reciprocal space? And so one way of doing this is by adding selenium defects. So it turns out that heavy atoms increase spin-orbit coupling on essentially any solid that they're deposited on. So I studied what is the effect of selenium atoms on the spin-orbit coupling. And as you can see, there are 3 unique defect positions on this carbon nanotube. And so the interesting thing is that if you look at this data over here, the spin splitting is dramatically different depending on where I put the selenium defect, right? If you look at this red position where I break this carbon-carbon bond, the spin splitting is much lower than if I look at this blue defect position where I don't break the carbon-carbon bond. So this begs the question, why, right? Why are these spin splittings so different for seemingly, these defect positions aren't that different from one another, right? So why is the spin splitting different? And so this was the question that I was tasked with answering over the summer. And so there are 2 different separate contributions to the spin splitting that I considered. And the first was what I just mentioned, this carbon-carbon bond, right? How does the lengthening of this carbon-carbon bond impact the spin splitting? And the second is the geometry of the selenium defect. How does the relative angle between these carbon positions and the bond length between the carbon and the selenium impact the spin splitting on this carbon nanotube? And so the most interesting thing, I think, is the first, the symmetry breaking property, where I considered the lengthening of this carbon bond. And using a tight binding model, as was mentioned earlier, I'm able to isolate the effect of this symmetry breaking property, and I get a really interesting result that shows that actually breaking this carbon-carbon bond or lengthening the carbon-carbon bond reduces the spin splitting. And so this is pretty interesting, I think, because in every other case that I can think of, breaking symmetry increases spin splitting. So this is a pretty unique result, and you can see that this D defect, where I fully broke this carbon-carbon bond, and in the other cases I didn't, has the greatest decrease in the spin splitting. So there is some correlation between bond breaking and a decrease in spin splitting. And yeah, so this was by far the most interesting thing that I found. The second effect that I mentioned, the geometry of the selenium defect, is like you just model it. It's not that crazy. It's like you just do it. But this effect was much more interesting. So yeah, I'd like to thank ASF for allowing me to present my research, and I'll take any questions.
Thank you. Who has a question for Ishan?
Excellent talk. I was curious if you did all of these measurements, if your carbon nanotubes were sorted by their radial size, and if you think there would be any effect if you went up to like a really wide carbon nanotube that was less stressed versus like a very narrow one.
Yeah, so I should preface, this was all computational, but you're right. So the data I presented is for a 4-2 carbon nanotube, which has a diameter of like 0.5 nanometers. And that has a much larger, if I can go back, that has a spin splitting around 0.2 or 2 MeV in the pristine case. But if you go to a bigger carbon nanotube, like 1.5 nanometer radius, that spin splitting is around 1 nanometer. 1 MeV constant throughout the Brion zone. So you're right. The smaller the radius, the larger the spin splitting. Yeah.
One more question?
Great talk. Do you have any comments on the distribution of the different morphologies of how the selenium atoms are binding? Because you have 3 different kinds of mining, but do you know how often those show up? Has anybody really investigated how often those are distributed?
Yeah, so I know we have a collaborator who does the same thing with sulfur, and sulfur's in the same column of the periodic table, so it shows the same binding trends. But as I understand it, it's random how it deposits, but actually, this is crazy. You can wrap DNA around the carbon nanotube, and that will, since the DNA is also helical, it will select only one defect position, one like L line, the red, green, or blue. It'll select one of those positions, and then you will be able to select which one you put on. So that's, yeah. Exactly, where you start wrapping the DNA. Yeah, it's really crazy, but yeah.
Thank you. We'll have a DNA wrapping workshop later, but thank you so much, Ishan. Now let's welcome Brooke Rogachuk, and we're going to talk about hydrogen gasification plant deployment. Woohoo!
Yes, thank you. Hello, everyone. Good morning. My name is Brooke Rogachuk. I'm a senior at the University of Oklahoma, and today we're going to talk about the best way to make hydrogen. But first, before we get there, let's talk about hydrogen. It holds a lot of energy in a super small space, and it kind of makes it a really valuable chemical. And so it can be used in a variety of different industries, and it has no carbon at the point of use, which kind of identifies it as the quarterback of a lower carbon future. But hydrogen has been identified as the fuel of the future since 1923. So nearly 100 years later, my study kind of evaluates where we're at today and figuring out how close are we to getting hydrogen in the system. So how do we do that? We're going to first look at GIS, so graphical information systems, and figure out where the best place is to have hydrogen. Then we're going to look at the best process to make hydrogen from wood, and then we're going to also evaluate the ways to transport it and all the economics and environmental assessments that go along with it. So first, we'll start with the graphical information systems. So right now we're looking at the Mid-Atlantic region, and we're evaluating based on these 9 factors. So the key ones here are forest biomass. So right now we're looking at the feedstock, or what we're going to make our hydrogen from, and how much of it is there. So we see lots of it in this area in West Virginia, and a lot in that little lower Maryland there. And then we have all these other indicators. And those all come together to make this graph. And it just says where the best location is to make hydrogen. And we see a lot of green right down here in this lower corner of Maryland. So Maryland's the best place to make hydrogen. Now that we have the best place, let's figure out the best process. So what we're looking at is gasification, which is just a fancy term for how we're going to take wood and turn it into hydrogen. And we're looking at 3 different types here. So we're looking at hydrothermal gasification, which is our first one. Then we're looking at steam gasification, chemical looping gasification, or CLG, and then we're looking at steam gasification with carbon capture. And we're looking at the economics right now. So we're figuring out how much does this realistically cost to make. And we're seeing that chemical looping gasification is actually our cheapest option, coming in at about $1, and this is in levelized cost of hydrogen. This is not what they would sell it for. But we're doing pretty good in terms of pricing for hydrogen. Now, we're going to look at the environmentals. So we've got 9 indicators here, and we only actually see our systems flagging on 2 things here. We've got global warming potential and photochemical oxidization. And so we see actually that chemical looping gasification, or that CLG again, is our lowest performing in carbon emissions, which is what we're kind of looking for when we're talking about making hydrogen. So now we know chemical looping gasification is going to be our best option in that southern Maryland location. Now, transportation. One of the hardest parts about hydrogen is figuring out how to transport it, because it is a gas, and it does a lot of different things, like moving around. So we've got 3 different processes evaluated here. We've got, first, this gas is packed into a tube trailer, and we're looking at the economics again, but we're looking at them based on increasing distances and also the amount of hydrogen we're transporting. And we're not actually seeing a big difference in pricing based on the amount that we're transporting, but we're actually seeing the major thing based on how distance we're transporting. So we've got these tube trailers, these pipelines, and then we're looking at liquefaction as well, so storing it as a liquid and then taking it into a tanker. And we're actually finding that pipelines are the best economically, I know, I'm sorry, it's hard to read, but the best to see here. So it's the best at a long distance, and we're seeing our tube trailer perform best at short distances here. So for long distances, pipeline, short distances, we want to do a tube trailer. So really, what we've just discovered today is the best place to have hydrogen is in southern Maryland, using chemical looping gasification, and using pipelines for long distances and tube trailers for shorter distances. And the real benefit of this study is that this can be performed anywhere with any technology. So it's not specific to just hydrogen. Of course, that's our case study here today. But we can use that for any chemical process along the way. And so that's kind of the really unique part about my research. It can be used for anything. And with that, I'd like to thank my professor, Dr. Judah Cooley, who refuses to have his picture taken with me. So this is what we get today. And the Astronaut Scholarship Foundation for this opportunity to speak to you all today.
Oh, thank you, Brooke. We have a couple questions, front row.
Is this only does this system only work for woody biomass systems, or can you also consider other cellulosic biomass like switchgrass or other something that could be produced in the Midwest and not just in regions where you get enough rainfall for forests?
Yeah, so it can actually be used for anything. The reason that we used wood is not pictured here. We did a whole long study about the best feedstock for that region, so we found that wood was the best for that mid-Atlantic region just based on what was available. But we can use any kind of feedstock depending on what region we're in. And that's kind of the benefit of this study, is that we can do that for every region that we're in and figure out the best ways to make sure that our plants succeed.
Thank you.
One more question.
You spoke a lot about the economics of transporting hydrogen, different distances, different ways that you can do it. When you guys were studying the economics of that, does that take into account like the danger of transporting hydrogen, just from a like it might blow up if it leaks perspective?
Yeah, so we did look, again, not picture, there's a lot of economics to go behind that, and it would be very boring for me to go through everything that we do economically. But we did look at that. We look at risks. We also look at what happens if a driver gets sick, what happens if we lose a tank for a day. So we did a lot of economic evaluation behind all that, and we also did sensitivity analysis, which is another kind of economic evaluation that we look at what are the most high-cost indicators. So when we look at this transportation, we look at what are the things that could go wrong and how much that would cost. So we did evaluate that, and that is a very major concern as well, yes.
Thank you. Blowing up is not good.
No, let's not do that today.
Not a good economic result. Brooke, thank you so much. All right, next we get to welcome Boston John about kinetic takedown methods. Welcome, Boston.
All right, good morning, everybody. My name is Boston John. Yes, that is my name. I'm a mechanical engineering student at Utah State University, and since fall of 2022, I have worked at Space Dynamics Laboratory. Now, I know this title might be intimidating. I promise this is the most complex part of the presentation. Kinetic takedown methods just means physically knocking something down. All right, so 10 years ago, if you saw a drone flying around, it was probably carrying a GoPro or maybe annoying someone at a park. And while that still might be the case, in 2025, drones are used for different things. In 2025, you can also use drones to play with your dog or take them on a walk. And while I would love to be presenting about this, my work's a little bit different. In the past few years, we've seen drones go from toys, like recreational toys, to tools for tactical warfare. More recently, we've seen how effective they can be in a swarm. So maybe think of like a swarm of bees coming at you. A swarm of drones is very effective in a tactical situation. They're very difficult to detect. They have a small radar cross-section, as you can imagine, and it's easy for them to overwhelm modern defense systems. And next to that, they're cheap, they're easy to build, they're readily available, and that makes them perfect for modern warfare. So of course, this begs the question, how do you stop a drone swarm? Okay, so I can't tell you that. As you can imagine, I mean, you can see down here, this is what I was approved, right here, this blank slide. But there's a few things they were gonna let me talk about, so we're gonna go over those instead. I'll keep you guessing. Okay, so what is Space Dynamics Laboratory? So SDL, as we call it, so we're a university-affiliated research center. We call it a UARC. And so essentially that means we are a strategic DoD research station associated with Utah State University and the Space Force. Primarily, we're focused on instruments and sensors for space. So we do a lot of work with JPL and things like that. Unlike a normal contractor, we are research-focused and we do a lot of highly customized deliverables. So, okay, so if we're doing all this space work, why do we have drones? That's a great question. A lot of our drones are used for sensor testing, so we'll attach an instrument or a sensor to a fixed-wing drone or a heavy-lift hexacopter and gather data that way. We also do the counter-UAS research. And to clarify, yes, so we work with both fixed-wing aircraft, like the one you see here. This one's fully 3D printable. Feel free to ask me questions about that. We also work with rotorcraft, so for those of you who don't know, that's like your more traditional drone. So if it has 4, it's a quadcopter. If it has 6 blades, it's a hexacopter. Let's see. And so, if you can't tell already, this is not like your guys' research. This is a very different environment. We work very quickly. To give you an idea, we go through ideation. You got to come up with your idea, right? And then we'll go into development. And then we'll go into testing. And sometimes this all happens in a week. We'll move from idea to idea. Sometimes it's a couple of days. Sometimes it's a month. It never slows down. And so coming up with an idea is a really big part of our job. And it's important to have a unique idea, but it also needs to be obtainable. It can't be years worth of work. It needs to be able to be done in a short amount of time. And so we look at past projects and research papers from other universities, and I'm sure you can imagine a lot of it comes from current events. And so once we get this idea, I sketch it out on a piece of paper or whiteboard, and I model it, and then I fabricate it using composites or 3D printing or sheet metal. And then once I do that, I have to see how we're going to test it. So sometimes we need new instruments. Pictured here is a load cell. For those of you who don't know what a load cell is, this setup is just going to measure how much lift it's taking. It's the same thing you use in like a bathroom scale to see how heavy you are. To give you an idea of our speed, we decided we needed a load cell like a Monday afternoon, and we were testing this by Wednesday. We designed a whole cage setup and everything. We're gathering data. So once we do the testing, a lot of it takes place indoors. We have a nice indoor testing area. Gather data. Our larger flights, you can imagine, are outdoors off-site. Sometimes we do need to do special cases. This spring I constructed this massive outdoor testing cell. It's 30 feet by 30 feet by 20 feet, hanging off the light poles in the parking lot for like 3 days, and then we put it away to never be seen again. Very fun project. And so yeah, so we have an 18-building campus near Utah State University. It's very pretty there. And so in the future, there is an increasing need for counter-UAS technology to keep up with the drone swarms. Current systems need to be improved. This is rapidly developing technology, and I hope to be a part of that in the future. I've loved my 3 years at Space Dynamics Laboratory, and I hope to keep working there in the future. And so in conclusion, I'd like to thank Space Dynamics Laboratory and Utah State University and Astronaut Scholar Foundation.
Thank you, Boston. How about a question?
Yeah, don't feel like you need to go into specifics, obviously, but I see, obviously, you're doing flights indoors. How are you guys addressing especially with counter-UAS, the problem of GPS-denied environments and
That's a
obviously
great
being able to track
question.
things?
We are addressing it. I think that's all I'm allowed to say. So, good question, though. Good question.
How about another question? That won't get answered. Go ahead.
So if you can talk about this, does your work focus on one or the other more so with piloted drone operations, so someone with FPV goggles or line of sight, or more on autonomous drones where they're doing their own thing, or some combination of both?
I don't think I can directly answer it, but I will say the division I work in is called Sensing and Autonomy. So that.
I'll go figure from that. Thanks.
Thank you.
Thank you. Oh, between the swarming drones and the bathroom scale, let's move on. Scary stuff. Reagan O'Neill, welcome. Low-cost boom systems. Welcome, Reagan.
Oh, perfect. Hi, y'all. My name is Reagan O'Neill. I'm a rising senior from Clemson University, and I'm going to be talking to you about rocket science today. So I work with something called the Sounding Rocket Program. So sounding rockets are surplus military missiles. We remove their warhead and then we use them for science. So I work with a Terrier missile. So this is an old Navy, like 1960s missile that they reuse. And that's actually a picture from a launch I was at last year. So I'm the lead engineer for something called NASA GHOST. This is a project to study the mesosphere. So this is a collaboration between Andøya Space Center in Norway and NASA Wallops. They're using this as a form of diplomacy to try to really coordinate between ESA and NASA. So my research group is a plasma physics group, and we particularly study the ionosphere. So it's this big, giant soup of ions and particles and plasma that we want to better understand. So all of your communications actually bounce off of the ionosphere, so stuff like radar and satellites all have to communicate through this region, and understanding this better is really important to making sure that our communications will run as we expect. So one of the really unique things about sounding rockets is they have something called a skirt. So if you look at the exposed payload right there, it'll actually blow off when it reaches a certain altitude, so we can actually directly have contact with the atmosphere. So this is really important for our instrumentation, but there's a really clear need for deployment systems because there's so much electrostatic charging and movement that happens from the rocket launch itself, but also from something called the triboelectric effect. When you pull your clothes out of the dryer and everything's really staticky, imagine that on the surface. It really messes with your electronics. So the problem with this is for a lot of labs, it's really cost prohibitive. So anything with NASA is a lot of things have to be flight qualified. So if we wanted to buy something to go fly on one of these rockets, it can cost anywhere from $50,000 to $200,000 per instrument. So I found a way where I built each one for about $100 to $200. So the telescope is about $100 without the instrument, and then the pads is about $75. And then our instruments themselves we can build for anywhere from $50 to $75. So NASA gives you a really giant deck of what you have to design with. So on the left is a summary of our key constraints for NASA GHOST in particular. We have a really small design envelope, so our things have to be really small and really low powered so we can get the most out of our instruments, and we don't have a lot of weight to work with, which makes it really hard to build something or just buy it off the shelf. So if you look on the right, that's the August testing operations. So anytime we design a new system, we have to actually drive up to NASA and test it on one of their bays. So there's a long list of tests we have to pass. So NASA really doesn't want our things to fall apart when we're at launch. So what we have to do is go in these really harsh testing conditions where we can go from anywhere from 10 to 50 Gs of loading under our deployment systems. So this is a Langmuir probe. It's really small. We're actually using current to measure electron density and temperature. This needs to be in direct contact with the ionosphere when we're measuring things. So we already have expected results from other studies of what we should see with changes in altitude. It really depends on time of day, so our graphs are going to look a little bit different, but we want to see the overall change in altitude. So we haven't predicted plasma density and temperature. The probes are extremely sensitive, so having really good deployment systems is important. So our HF receiver, like the Langmuir probe, also is measuring electron density, but we're using radios instead. So we're using an antenna to actually measure something in Russia. So the Russian timing station is outputting radio signals, and we can pick them up throughout our rocket flight and use that math to better understand what the electrons look like in that region. So also, like the Langmuir probe, you're going to see a really similar trend with altitude that we can actually use to make sure that our data is collecting as we expect. So this is what our system CAD looks like. So CAD's computer-aided design, which is a way of we can build everything on a computer before we go and prototype it. So the telescoping boom is what we're connecting to the Langmuir probe. We call it the PADS. It's the Passive Antenna Deployment System, and that's what we're using for our antenna to measure the Russian timing station. So this is what it looks like. It's a little ugly, but when everything's deployed, it's going to look something a little bit like this. So for the telescoping boom, we use a brass rail cam system. So that's going to be what's going to extend out our Langmuir probe. And I don't think my videos are working, but it extends out pretty fast. Yeah, that sucks. Okay. Well, the passive antenna deployment system is we needed a really cheap source of spring steel. So we need something that's called a shape memory alloy. So we need where we can bend it and have it extend back out to what we expect. So tape measures they're super inexpensive, and we can strip them and then use them to make a really cheap antenna. And we can run a couple tests on it to calibrate that to make sure it'll work for our system. So we use something called a nichrome burn wire. So what that's going to do is we're going to keep our system in that little box up until the rocket sends a signal to our system, and it's going to cut the line and open it. And my videos are working. But we're going to be launching in Norway in November, which will be really exciting. I get to go to the launch pad. And this is just some publications and presentations talking a little bit more about what we work on. And I just want to say a big thank you to my research group and all the people who really helped make this funding possible. And just a special thank you to ASF.
Good. Thank you so much. We have a question.
Hello, great talk. At what point during the suborbital trajectory will the boom deploy?
We're actually trying to deploy it as soon as possible. So the second the skirt blows off, I think it's about 180 seconds, our telescoping boom can deploy, and the antenna is going to deploy a little bit after that just to minimize the loading on it so you don't get those kinks you see with tape measures.
Great. Reagan, thank you so much. All right, next we are going to welcome Elizabeth Romero. Hi. Optimized Medevac Ops.
Thank you all. My name is Ellie Romero, and today we'll be talking about the application of lower body negative pressure to inform optimized medevac operations. That's a lot of words. A more straightforward title is how to ethically collect data on people bleeding out. So that's a lot, right? So we're going to take a step back and we'll work our way up to this problem. So a little bit about me. I am standard-wise an engineer. I love my rockets and planes. However, I am deathly afraid of a desk job. So I love real-time operations. I'm out of my desk doing real, tangible things, working with people. And then some random fun on the right. Today we'll be talking about the first two columns of my life, engineering and operations. And the combination of those two has brought up some really interesting questions, such as, how can we optimize aerial medevac operations? Operations planes, right? Combination. So this isn't just a thought experiment. This is quite real, and there are some good critical cases. For example, hemorrhage. It is the leading cause of preventable military death and the second leading cause of trauma civilian deaths. And so this is a very critical case, and we need to better understand how to optimize these evacuations to get people to safety. However, there is a balancing act. We talked about two columns, the engineering, the operations. So if I put my operations hat on, my EMT hat on, I'll say, okay, well, there's the golden hour. So the best way to improve patient outcomes for trauma patients is to get them out as fast as possible and get them to a trauma center. But then you put the engineering hat on and you're saying, okay, if we're going really fast and we're taking aggressive maneuvers, these patients are going under really high Gs. And those high Gs might exacerbate the patient's injuries, and we don't want them to get even worse, right? So it's a balancing act of how fast can we go safely. And we don't really understand that relationship very well of hemodynamic instability and acceptable G forces. And so that's why we get back to this question. We need to figure out blood loss, Gs, how do we do that ethically? We can't just cut people up in the name of science, right? So the answer is we put the engineering hat right back on. There's a device called LBNP, lower body negative pressure. A lot of words, but all it is, in essence, is you're putting a vacuum on the lower part of your body, and it's pulling blood from your upper body down to your legs. And so your body thinks you're bleeding out because you've displaced the blood in your central circulatory system. But it's fairly safe because if you just crack open the seal or press a button, all the blood comes right back up. And so a little bit of engineering, that's my friend Eddie at the MIT Aerospace Physiology Lab. But proper engineering, just going through the steps, we have our requirements mostly driven by the plane we're using and keeping people safe, right? So we have our requirements, we make our design, analyze the loads to make sure that it will work with the plane, work with the different frequencies, work with the loads, and then I put it together. We then went to Holloman Air Force Base with the 586 Test Flight Squadron, really lovely people, and we integrated onto a C-12J. Then we went to Edwards, really good cross-road trip, right? Boston, New Mexico, California. Then in California, we went to the test pilot school where really brave people volunteered to get the blood taken away from their heart and do this for me, and they were really eager to do it, so I'm really grateful for them. The test pilots are lovely people. And so then we did some ground testing for all the participants to get good baselines, and then we did real test flights and got some good data. And for the reference, every test pilot campaign, they have their own projects, and this was made by like grown test pilots, like Magic School Bus, Kermit the Frog, all their idea. So some future work, now that we've collected all this data on G-loads and different levels of simulated hemorrhage using different levels of pressure on that by the LBMP pressure gradient, we now have all this really beautiful data. And so now we get to make an algorithm to really figure out what is the optimal flight profiles that we can take given patient status. And keep in mind, while we were on that plane, we had a whole sensor suite to collect all, like, lots of good data, but also really track if we're hitting our, like, termination criteria, because safety is the most important thing. And then also, this could be used in space applications, because when there's no gravity, the fluids come up, and it puts a lot of stress on the person's head, eyes, and such. And so this could be used to alleviate a lot of space symptoms. Thank you very much to MIT, the 586, TPS, ASF, lots of acronyms, and last but not least, the Leslie Way Foundation for sponsoring my scholarship. Thank you.
Wow, that was a lot of blood and death and all kind of business. But who has a question for Elizabeth?
I do.
Hi.
We flew LBNP on my first mission, STS-90 Neurolab. Did you work with NASA at all on their LBNP procedures and facilities that they had?
That's a good question. The short answer is not directly for this project, but a lot of the people involved in my lab did consult with all the NASA folks and get review standards and make sure that the data we're doing is like novel and could be applied to spaceflight. So a little bit, I've had the honor of working with them a little bit after the project, but this is a continued effort, and so we're really optimistic for new partnerships.
Thank you. One more question.
I was wondering, maybe this is a silly question, but
Very silly questions.
I feel like if you're addressing wounds and transporting patients, what if the patient has a wound on their lower body and then you vacuum all the blood there?
Yeah, that's a great question. So the data that we're simulating, like the kind of hemorrhage that is very like central hypovolemic, and so it's very much like chest wounds, and that's just like, it's easy for us to simulate, and in future, I guess we can go the other way around. But yeah, that's what our scope was.
Great. Thank you so much, Elizabeth.
Thank you.
Okay, next we're going to welcome Kevin Shu, and he's going to talk about engine inlet distribution. I got a preview of this last night. It's awesome. Let's talk about turbulence.
Hello, everybody. I would just like to say that I came after Eli. Eli is doing some great work, doing life-saving people in the air, helping our troops. I'm just over here making sure Eli gets the places she needs to go. But anyway, I'm Kevin. I go to Virginia Tech, and my research is on engine inlet distortion, validation of subscale stream vanes through particle image velocimetry. A little bit about me. As I said before, I go to Virginia Tech, and I major in aerospace engineering and mathematics. I also work in Virginia Tech's Advanced Propulsion and Power Laboratory. It's not moving forward, sorry. Technical issues, there we go, thank you. So before we start getting into the technical stuff, I would like to just ask an easy question for you all to think about. Which straw is the easiest to breathe through and why? You know what, let me just show you here. So here I have two straws. I have two straws. I stole them from the Omni Hotel, so please don't kick me out, please. But yeah, these straws will represent our engine ducts. And what I'm actually doing is I'm gonna bend one. You can hear that. Yeah, and now I'm gonna breathe through them. Not bad at all, pretty easy to breathe through the straight straw. Now this straw right here, the bent straw, that was a lot harder, yeah. And so it turns out that we can apply this analogy. Well, okay, that was pretty obvious. I just demonstrated my experiment there, but We can apply this analogy to jet engines as well. It turns out that because jet engines are sucking in air, just like you and I, they are just as affected by the bent straws as you and I. And you can see here, that's his S duct, and the S duct causes the air to distort as it's going through, which causes this bent straw inlet distortion effect that we are researching. Like I've just demonstrated, jet engines like uniform, steady, and perpendicular flow, aka the straight straw. This is flow that is not changing with time and has the same direction at all points. However, when that doesn't happen, we get something called inlet distortion, which can cause inefficiencies, vibrations, and in the worst case, engine failure. All aircraft experience inlet distortion to some degree, but aircraft with unique body geometries, such as stealth fighters and next-generation transports, such as the hybrid wing body, are especially affected. Now, we need to simulate this inlet distortion of a corresponding aircraft on its engine. We could spend a small price tag of about $100 million and get a new aircraft to put the engine inside. By the way, if any of you have that kind of pocket change, please let me know after this presentation. But for those of us without that kind of money, we make do with inlet distortion generators, an example of which is the stream vane, which is mounted for the engine and generates a distorted velocity profile that is then ingested by the engine. This is used in all of industry, being used by organizations such as NASA, the Air Force, and all major engine manufacturers. Of course, we also need to validate the stream vanes themselves before we even put them on the engine, just in case to generate that weird, wacky distortion that damages the engine. Therefore, we bench test them by putting them on wind tunnels. But this leads to a new problem. How do we get the diameters to match? It turns out that we have to scale the stream vane up or down to match the diameter of the wind tunnel. This leads to the questions that my research strives to answer. Is the inlet distortion profile similar when we scale? And more importantly, does this scaling generate any unwanted modes that are forced into the flow? Oh, sorry. And so this is how we will answer my questions. We conduct our tests in Virginia Tech's high-speed wind tunnel utilizing an advanced technique called particle image velocimetry. Next, we use data analysis to find and isolate these distinctive flow features. Of course, a picture is worth 1,000 words. Here's us seeding the flow with a lot of smoke. You can see all the smoke coming out of the wind tunnel right there. Yeah. Next up, this is us turning on the laser. Yes, it does look radioactive. Don't worry, it's not radioactive. And finally, this is us actually running the test. Notice in the flow on the right, notice in the video on the right that you can see the swirling of the smoke in the wind tunnel. This is exactly what we're looking for, basically the first dominant mode. Of course, we have captured some very, very remarkable results that have caught the attention of engine manufacturers, and because I do not want to be dragged off this stage by the FBI, I will not be able to share them here. However, I can assure you that I've isolated very, very distinctive stream vane flow features that will also allow us to scale up, and that will also guide future research into scaling up and the scaling down of stream vanes. All this leads to more accurate, cost-effective inlet distortion generators, as well as a better understanding of engine inlet distortion, ultimately leading to aircraft that are more efficient and effective to meet the needs and missions of tomorrow. Before I close, I would like to acknowledge a few groups of people. First and foremost, my amazing PIs, Dr. Todd Lowe and Dr. Joe Gonzalez, as well as the amazing stream vane team I've had the privilege of working with this summer. I would also like to thank the Advanced Propulsion and Power Lab, as well as the Astronaut Scholarship Foundation, for not only providing me with funding, but also the motivation and inspiration to continue my research. Last of all, I would like to thank you for listening to my presentation. If you'd like to contact me afterwards, my contact information is on the screen. And once again, thank you all so much. I will now open the floor for questions.
Thank you, Kevin. Who has a question?
Kevin, great talk. That's
Thank
really
you.
interesting stuff. I know you are not going to be able to go into like what you've actually been able to see. I'm curious with like the range of testing that you've done. I noticed you had one CAD model up there, but I assume you guys have gone through many, many different kinds of flow disturbances.
Right.
I'm curious about if you've seen a lot of similar patterns between very different kind of filters for your airflow.
Okay, I would love to answer that question, but again, I do not want to be dragged out by the FBI, so I will not answer that question. I'm sorry.
One more question for Kevin.
Yeah, I had a quick question about here. Yeah. Are there any, because this seems like kind of fluid dynamic stuff, but is there any like computational stuff going on as well, like modeling, or is it all like kind of done in wind tunnels, lab type of stuff?
So it's actually a combination of both. What we do is we use PIV to gather the velocity data, and then we put that data into a lot of like custom computer programs running data analysis techniques such as proper orthogonal decomposition, dynamic mode decomposition, and other data analysis techniques to then isolate these specific modes that occur in both space and time. Did that answer your question?
It does. Thank you.
Thank you.
Great. Thanks, Kevin. There's a van outside waiting for you. Really good. Now, let us welcome Emily McHale, and she's going to talk with us about flow patterns in a hybrid motors.
All right. Hi, good morning. My name is Emily McHale. I'm from North Dakota State University, majoring in mechanical engineering and physics, and I'm going to talk to you about seeing inside a hybrid rocket. So before we get into talking about a hybrid rocket, we should talk about the parents of a hybrid rocket. We're used to solid rockets and liquid rockets, so there are benefits and pros and cons to both. Both are dangerous, both are great. But so when we're thinking about a solid rocket, I like to think of a firework. They're great because they have high thrust, but the problem is once you light them, you can't throttle them, and once you turn them off, they can't be restarted. We think about liquid rockets. Once again, we have high power, they're highly flammable. We can control the thrust, we have throttling capability, we can shut down and restart them, but they're highly flammable, often have cryogenic components that have very difficult insulation systems required, and just overall, they're more complex. So enter the hybrid rocket. The hybrid rocket, I like to call it the best of both worlds. So with a hybrid rocket, we have a solid fuel with a liquid or a gaseous oxygen, sorry, I'm short. Solid fuel with a liquid or gas oxidizer. They're usually more reliable because we have fewer degrees of freedom than like in a liquid propulsion system. We have fewer pumps and fewer areas for leaks. There's no accidental mixing of components because the solid fuel is on its own, completely separate from the liquid or gaseous oxidizer. The fuel on its own is inert. It won't combust without the oxidizer flowing through. Throttle. We have the capability to throttle like a liquid rocket. Think again about that firework example. We don't have that problem. It's safer to store. Since the solid fuel is stable on its own, it's safe to store at room temperature. It's much safer to transport and store. You can almost ship it like you would like a chunk of plastic. Oftentimes, it is just a common material like ABS for 3D printing. And then finally, lower cost. It's a much simpler design. We'd have more common everyday materials like that ABS that I mentioned, and the materials are much easier to come by. Anywhere you can find some kind of plastic or a Praxair air truck, you can make a hybrid rocket, but maybe look into it first. But okay. So next, why do we care about performance? Why even measure it? So knowing a hybrid rocket motor's fires is not enough. We need to know how well it works. Solid and liquid propellants, as we know, have pros and cons, but we need to know how does a hybrid rocket measure up. If our goal is to optimize the design of a hybrid rocket, we need to first understand what it does, why it does what it does. This comes from both qualitative and quantitative characterization. First, we want to know from a big picture point of view, how is the machine performing? Is the ignition reliable? Sometimes it's not. How responsive does it appear to be to throttling? What is the shape of the exhaust flow? Then we move to quantitative results. Thrust, chamber pressure, fuel regression rate, specific impulse, all those important things. One of the biggest concerns in hybrid rocket design is the geometry of the combustion chamber. So as we change the geometry of the combustion chamber, how does it affect the fuel grain regression rate? And that's a big concern for our research. So enter the NDSU HRM, the North Dakota State Hybrid Rocket Motor. So the NDSU HRM has a polymethyl methacrylate, PMMA, acrylic fuel grain, and uses gaseous oxygen as the oxidizer. The coolest thing about our hybrid rocket is it's an optically clear combustion chamber, which means we can see inside the combustion chamber in real time all throughout the firing, and also in between tests, we don't have to cut open the combustion chamber to see how the fuel grain has regressed over time. And this is really the backbone of our research, so we can take those high-speed images and get real-time data of the combustion happening inside. So studying the flow, there are a couple different ways that NDSU has studied the flow. We've done some preliminary PIV. We're now moving to Rayleigh scattering for our next focus, but today I'm going to talk to you about tomographic imaging. I like to think about tomographic imaging as like an MRI for the rocket, which is essentially what it is. So if anyone's gotten an MRI, just imagine we're sticking this rocket in a big donut that makes noise and, you know, takes pictures. It's not quite that complicated, but as you see here, we have cameras that are at different angles, and you can take the angles that they're 2D images, right? We can take those cameras at angles, take those images, and create a 3D reconstruction of the flow. Here's just a video of the firing. Wow. Super cool. Oh yeah, that's the stuff, right? So here, so we have 4 cameras in our setup. This is a vertical setup. We do a horizontal and a vertical setup, but the vertical setup is usually better for seeing like the axis symmetry of the flow. This setup is around the exhaust, and we do the setup around the exhaust and the combustion chamber. If we had more cameras, we would do more frequently. But all right, speed run it. So tomographic image slices, basically we put that into a mathematical algorithm. We're able to get a 3D reconstruction. The good news is, in the exhaust flow, we were able to see the Mach 2 diamonds as we would expect. Our nozzle is designed for Mach 2 exhaust flow, and the diamonds that we observed reflect this. Here's the combustion chamber. It's a 5-second test, so this is slowed down, sped up. It's actually black and white, but we made it red to look cool. So key things for the combustion chamber. Number 1, we noticed stable combustion. There were no sudden pressure drops, no dangerous oscillations, which is good news for both performance and safety. And then with that transparent fuel grain, we're able to actually see the flame front and the flow structures moving through the chamber. And the biggest thing we notice here is we've got this more streamlined laminar flow at the beginning. So this is the inlet of the combustion chamber, and then we've got the nozzle down here. So we've got the streamlined laminar flow, and it becomes more turbulent, which, as we know, the more turbulent flow causes a higher rate of heat transfer. And this, I think, is one of the most interesting things. This is what the fuel grain looks like at the beginning of a first run. Our burn is pretty much uniform. It's just a cylinder in the middle, and then we see that higher rate of fuel grain regression further down the chamber. Why this matters for the future. So if we have a better understanding of hybrid rocket performance, we're able to make improved designs, not only physical designs, but also mathematical models. If you've ever tried to model a hybrid rocket in CFD, it is a pain, and especially when it comes to fuel grain regression rate, it's constantly changing. We have models, but we're just trying to understand that a little bit better. And then finally, that can lead us to safer, smarter, more efficient propulsion systems. And finally, I want to thank the Astronaut Scholarship Foundation for giving me the opportunity to speak to you all today and for this amazing weekend. I want to thank North Dakota State University College of Engineering, my mentor, Dr. Jordy, our Small But Mighty lab. We've got one more that's not pictured, but Small But Mighty, and the North Dakota Space Grant Consortium for our funding. Thank you.
Thank you. Okay, we're one question away from a break, so who's got a question for Emily?
Hi, Emily. I was just wondering, you were talking about using like solid propellant motors.
Yeah.
How does the degradation or the regression of the fuel, I know that increases surface area, burning area, how does that impact thrust?
Oh, this is an excellent question. So this is something we're actually trying to look into at our, kind of in our next coming papers. Our rocket is a solid 8 pounds of thrust, so look out. But and it's a pretty consistent. I didn't include it in here, but we have a pretty consistent thrust curve. We have a little bit of a peak at the beginning, but not really. But I haven't worked as much with solid rockets, so I can't give you a super great answer on that. But that's definitely something we're looking into in the future. Thank you.
Thank you. You were all way too excited about that MRI and video and all that business. But yay. Thank you, Emily. Very good. Nothing like that has ever happened in any one of my MRIs, just saying. You all have seen a phenomenal first half of this technical session number 3, and now it is time to refresh your coffee. So 10 minutes exactly. Thank you for coming back. We're going to have a great second half, and introducing Cameron Kelly. Welcome.
Kelly, and I'm a cadet at the United States Air Force Academy studying astronautical engineering and Russian language. Today, I'm honored to share with you my research on orbital debris modeling and mitigation, why it's an urgent issue, how we can address it, and what role policy, technology, and international cooperation play. This project focused on 3 major objectives, and this is a project that I'll be continuing throughout my cadet career at the Academy. First, understanding the current state and causes of orbital debris, what it is, where it is, and how it got there. Second, evaluating some mitigation strategies. This is what I'm working on this semester, both technical and policy-based, to mitigate future risks. And third, I'm going to visualize the scale of the problem by analyzing real satellite data, and we'll get to see some of those graphs today. I used both qualitative research and quantitative analysis, and I did some case studies on Starlink, and then looking this semester at the gap between the policies that we currently have and the technological tools that are available. To perform this analysis, I used the SATCAT database, which is satellite catalog maintained by United States Space Command at the 1st Space Operations Squadron. It's a public data set of all known artificial objects in orbit, and artificial just means man-made. It doesn't mean that they're fake. I wrote MATLAB code basically, and I data cleaned and visualized, and we'll see those today. And I segmented the objects by orbital regime, which is just the different orbits they're in. I'll explain those as we go through. This also wouldn't be possible without my research mentor, Lieutenant Colonel Luke Hagan at the Air Force Academy, as well as Miss Sandra Wilson, who helped provide me with some of the data, and as well as the Astronaut Scholarship Foundation for allowing me to be here and present today. So first, the results made the threat that we're facing very clear. Low Earth orbit is the one on the left there, and then I sorted it by state actors. So the first one we have in low Earth orbit is CIS, or the Commonwealth Independent States, also known as the former Soviet Union, so that's Russia. And they're in blue. And then after that, the United States and then the People's Republic of China are who have the most debris in orbit, in low Earth orbit. And these patterns reflect decades of launch activity, much of it before these modern debris guidelines were in place. And then now if we look at geostationary orbit, which is on the right here, that's a little bit farther out. Objects here orbit around 35,000 kilometers above Earth, and due to the lack of atmospheric drag, they don't deorbit on their own, and they will remain there for basically forever. And my analysis shows a dense band of debris clustered around 42,166 kilometers and low inclinations, which is where high-value communications and weather satellites operate. Although geostationary orbit is less crowded than low Earth orbit, its permanence makes it fragile, and even a small number of derelict satellites or rocket bodies, many of them launched before different protocols were common, that deorbit bodies can pose long-term risks to operational spacecraft. Next, we're going to look at medium Earth orbit, which is anywhere from low Earth orbit to geostationary orbit, as well as doing a little case study on Starlink. So this visualization in Starlink, most of their satellites operate around 6,500 to 6,600 kilometers in semi-major axis, so that's measured from the center of the Earth out, at inclinations of 53 degrees, 70 degrees, and 97 degrees. And what stands out is actually the associated debris, which is mostly from Falcon 9 stages and failed payloads, which appears at slightly higher altitudes, up to about 6,900 kilometers. This adds to long-term congestion risk in already crowded zones. And these patterns show that orbital congestion isn't hypothetical, it's happening now, and it's shaped by consistent national and commercial behavior. Similar clustering appears in medium Earth orbit, which is everybody thinks of as the oddball, but it's very important because navigation constellations that we use, like GPS and GLONASS, that the Russian Federation uses, that's where they operate. And why this is all important. Orbital debris threatens everything from space stations for astronauts to weather satellites. A single 1 centimeter object travels in low Earth orbit about 7 kilometers per second, and that can easily destroy a satellite. We've all heard of the stories of like the paint chips hitting the International Space Station, causing a lot of issues. And every collision creates even more debris, which increases the chance of future collisions. This runaway cycle is what we call the Kessler syndrome, and it's basically more and more debris. So one piece of debris collides into another, and it just creates a chain reaction of these collisions. And the problem with this is that eventually everything could become a debris, and the space could become a huge just debris field. And we've already seen it in 2009 with the Iridium Cosmos collision and China's 2007 anti-satellite test, which created over 140,000 trackable debris fragments. And we use space for everything, so it's very, very important that we try to stop this debris from happening. And some of the promising technical solutions, active debris removal, it's very similar to the naval industry, actually. We use nets, harpoons, tethers, and different AI systems. There's passive technology that can help deorbit these satellites, such as like drag sails and inflatable balloons. Another proactive solution can use nuclear propulsion systems to help deorbit, but there's a lot of global treaty and enforcement needed, which is what I'm working on this semester. And the takeaway is this, and that we can solve this problem, but it requires us to act now before the problem gets too bad for us to even act on it. The orbital environment is finite. Once it's too congested, we can't just clean it up overnight. Each nation, spacefaring company, and agency must take responsibility, which means stricter regulations, enforceable treaties, and better incentives for cleanup and compliance. Thank you. Are there any questions?
Thank you, Cameron. We have time for one question.
Thanks for the talk. With Kessler syndrome, is the timescale that we expect that to happen on something like many years where we expect to have good forewarning if we're headed in that direction, or something where we could pass a critical threshold and have it become much more severe in a course of weeks or days?
Yeah, so it's very hard to model exactly when it's going to happen. There's different estimates. Some estimates say 10 years, which would be like the worst case scenario, and some estimates are more on the scale of 200 years. But it's about what we are doing to solve it right now. If we don't do anything to solve it right now, there becomes a critical threshold that we reach, at what point the Kessler syndrome becomes inevitable. So Kessler syndrome is like worst case scenario, and then we need to be taking steps more and more to try and stop it. So my research is more focused on making sure that everybody knows that this is an actual problem that we're facing, and all the satellites that we use for like GPS, so anything like gas station pumps, using your credit card for anything is all run in space. So if we don't have that, it becomes a little bit of an issue.
Thank you.
Great. Thank you so much. Next, we would like to welcome Eric Mulder on enhancing cislunar mission design. Welcome, Eric.
Hello, my name is Eric Mulder. I'm an aerospace engineering and computer science student at Auburn University. And today I want to present our work on enhancing cislunar mission design using immersive visualization and interaction. So first, I want to give some background. So when you're working in cislunar space, you're doing space mission design, a key part of the process is what's called trajectory design. A trajectory, of course, is the path that a spacecraft follows. And in this research, we're specifically looking at ballistic trajectories. So trajectories of a spacecraft when they're only under the influence of external factors, gravitational forces, solar radiation, etc. And specifically, when you're doing trajectory design, two key challenges we're looking at are periodic orbit design, so finding conditions that result in a repeating a loop in your state space. So you come back to the same conditions over and over again, you're in an orbit, and then transfer design, so finding conditions that result in the arrival at a target state or typically a different orbit. Now, when you're working in cislunar space, there's a problem called the three-body problem. So you have three interacting bodies: the moon, the Earth, and your spacecraft. This is an infamous problem because it is chaotic, highly nonlinear, and there's no general analytical solution for the problem. That means you can't just take a spacecraft and figure out where it's going to be as a function of time, and instead you require complex numeric methods. And so typically, these targeting algorithms are two steps. So the first step is finding a guess, an initial starting point for what an orbit roughly looks like, and then doing an optimization step where you refine it and tweak it until it is a dynamically valid orbit. So on the figure, you can see the blue is an example of an initial guess for a trajectory, and the pink is a solution after optimization. That second part, that optimization step, can be handled very easily, or not easily, but it can be handled through known numeric algorithms. But that first part, finding that initial guess, is a much harder step, and there aren't a lot of good traditional methods other than just guessing or using an existing catalog. This is where the second part of our project comes in. So, extended reality encompasses both virtual and augmented reality. Virtual reality being a full replacement of a user's environment through a headset, and augmented reality being the interleaving of real-world and virtual elements. Both of these provide two key features we care about. The first one is stereoscopic visualization. So a VR or AR headset provides two little screens, and they use your natural depth perception. So you can look at a scene and understand the 3D nature of models in that scene using the same mechanisms we use to naturally perceive depth in the world. The other part is 3D interaction. VR and augmented reality systems use either controllers or hand tracking to allow you to naturally and intuitively interact with 3D objects in the world and manipulate things that a 2D mouse doesn't allow. So, by combining these processes, by using extended reality for trajectory design, we've implemented some approaches for doing that initial guess generation, where we build a real-time feedback loop of a human interacting with the state of a spacecraft through a position controller and a velocity controller, paired with real-time propagation of the spacecraft to show a live update of how the spacecraft is going to move based off of the manipulation that the user is doing. And this allows you to take advantage of human or like expert intuition for doing that initial guess creation very quickly. So we built a Unity. Unity is a 3D game engine. We built a Unity-based virtual reality tool for doing the trajectory design that uses a range of 3D interactions and visualization techniques for doing different things, one of which is the periodic orbit design. Here you can see is a picture of the application. So you can see there's position velocity controllers along with different buttons and interactables in the scene, and the user is going to put on a headset and interact with that using different controllers and manipulation. So, how is it performed? So we've done testing at our lab and at the Aerospace Corporation with experts in cislunar mission design, and we found these perform very effectively for doing design of complex orbits very quickly. So we were able to design orbits like these shown in a matter of minutes, which using traditional techniques we were tested, and they took on the order of days, weeks, or even months to design for teams. And so this is a significant speed up in how quickly you can do that initial guess prototyping for complex orbits. So, in conclusion, we think that extended reality, VR and AR, provides a very promising system for interacting with complex 3D structures. And when we're working with cislunar space, human intuition is a really important tool for building that initial guess and prototyping. In the future, we hope to work on problems in proximity operations, so doing rendezvous satellites close to each other, and we're working to design a unified system for a lot of different space mission design problems. I'd like to thank my research advisor, Dr. Gazzetti, the 3i Space Dynamics Lab at Auburn University, and the Aerospace Corporation for funding some of our research. Finally, I'd like to thank the Astronaut Scholarship Foundation, and of course, all of you for listening.
Oh, thank you. Thank you, Eric. We have time for one question for Eric. Ooh, fast.
Eric, really cool work. This is really interesting. I'm curious if you could just expand a bit on where you're finding your initial guesses. You were mentioning, like, we've gotten a lot of solved three-body problem stuff, like just catalog, with like integral tables. Have you been looking through those and then comparing your data with that kind of as like an experimental base point, or are you generating some of these initial models like in-house?
So the initial guess, right? So the point of the application is doing the very initial guess for an orbit. So if you're a trajectory designer, right, you have some idea, you want to go from somewhere to somewhere else, and you're placing position and velocity manipulation in the scene and just adjusting it and using propagation to effectively learn the system dynamics. And then that gives you your initial guess, and then you run it through an optimization algorithm to produce a final solution. We've compared it to like JPL's three-body catalog, and then we can just look at the like change in the Jacobi constant, et cetera, to look at things like that to validate our accuracy of results.
Cool, thank you.
Thank you. Thank you, Eric. So we have the pleasure to welcome Kavi Day remotely. So let's give her a big drum roll. Welcome, Kavi. We're glad to have you remotely. Welcome to Houston.
Thank you. Can you hear me?
We can hear you just perfectly. Why don't you go ahead?
Okay, great. Hello, everyone. I'm Kavi Day. I'm a senior at Harvey Mudd College, and I will be presenting on how we can understand the millions of new asteroids that are about to be discovered. Uh, oop. Up until this point, we found over 1 million asteroids in our solar system. This visualization shows some of those. Every asteroid is a point, and the lines correspond to planetary orbits. And when we observe an asteroid, that means that we're measuring its current position and its current velocity, which we can use to find an orbit that looks something like this. And when I say we find its orbit, I mean we fit an ellipse to the trajectory of the asteroid that includes a semi-major axis, or what I call radius, and inclination, which is the angle, and the eccentricity. But it turns out that this orbit doesn't stay constant. It actually changes slowly over thousands and thousands of years. And since we can't easily measure a single asteroid over thousands of years, we have to use computer integration. So if we integrate a single asteroid for 30 minutes of human time, that allows us to get 10 million years of asteroid positions in computer time. Once we have this 10 million year picture for a single asteroid, we can do some data analysis to that data, and we can find a single constant orbit that is a single set of 3 numbers, semi-major axis, inclination, and eccentricity, that uniquely represent that asteroid and all the ways that it can change over time. If we do this for every single asteroid we know about, then we get a plot like this rainbow one on the right side. In this plot, every point is an asteroid, the x-axis is radius, and the y-axis is inclination. And there's a lot here, but the important thing to focus on is the groups of points, or high-density regions, some of which are labeled in black text. These high-density regions correspond to asteroid families, which is something that we want to find because they help us learn about the history of our solar system. So just as an overview, we can take measured positions of asteroids, run computer integrations to get 10 million years of data, do some processing, condense that down to 3 numbers, and then make this kind of plot that shows asteroid families. But we can only do this if we have these constant orbits that we get from the 10 million years of data. If we try to make the same plot using the measured changing orbits, then we get something that looks similar, but all of the details have been blurred out. They've been spread out, so we can no longer see individual asteroid families in details. So what happens when a new observatory, like the Vera Rubin Observatory, comes online, which is expected to discover 10 million new asteroids? Well, if we just do some quick math, 10 million asteroids times 30 minutes of integration per asteroid is 570 years of computation. And this isn't a future problem. This is like a now problem, because Rubin has already found 2,000 new asteroids in its first 10 hours of searching. And even if we parallelize this, it still is kind of unfeasible to do on human timescales and at the rate that scientists want to understand these asteroid families. So what can we do instead? One solution is machine learning, which is what we've tried. And if we were trying to avoid this expensive computation, then we need to think about what the inputs to this machine learning algorithm are. Remember that what we measure are the asteroid's current orbit, which we know is going to change. We can use some physics known as perturbation theory to estimate what the constant orbit should be. And this estimate for some asteroids is really, really good. For other asteroids, it ends up being quite bad and is many order of magnitudes off. But either way, it's an estimate. So if we take the measured changing orbit and the estimated constant orbit, we can feed these both to a machine learning model. In our case, we use a gradient boosted decision tree, and then train that model to predict the constant orbit that we want. And it turns out that this actually works pretty well. We can predict constant orbits in milliseconds instead of hours, and we can do this with an error of 1.6%. These two plots are similar to the ones that I showed a few slides ago. The plot on the left is the exact same. It's rainbow, and it's showing the true constant orbits of the asteroids calculated the expensive way. The plot on the right side is the same thing, but now we're using the output of the machine learning model. And what you can see here is that we fixed the issue of blurring. We fixed the issue of spreading out. All of the individual asteroid families are clearly seen as high-density regions, and we could have an algorithm or a human that goes through and picks out all those asteroid families that we wanted. So it's awesome that that worked, but this is just the first step of a whole host of tools that need to be made to analyze the petabytes and petabytes of data that are coming from the Vera Rubin Observatory. In addition to improving accuracy, one of the things that we want to work on is making a more general tool, because it turns out that finding constant orbits is not a problem unique to asteroids, but something we want to do for planets in other solar systems. For anything that's orbiting, you can kind of find a constant orbit. So there's a whole bunch of future work to be done on trying to understand orbits, and if you know the physics of it, you can think of it as a transform to action angle coordinates. I'd like to thank my advisor, Daniel Tamayo, as well as a student who worked on this project with, Leia Shen, and all of you for listening. Thank you.
Thank you, Kavi. We really wish you were here with us. Who has one question for Kavi?
Hi, that was a phenomenal presentation. Thank you so much for offering your valuable insight.
I just have a quick question regarding the orbital parameters. Why did you choose only 3 instead of the full 6 parameters?
So we only care about the shape of the orbit, not where the asteroid is along its orbit, which allows us to get rid of 1. But in addition, because we're taking this global 10 million year picture, anything that changes quickly, those changes get averaged out. So it turns out that we can actually kind of ignore semi-major axis in many cases as well, because the semi-major axis oscillates so rapidly that when you take a zoomed out picture, you can ignore all those oscillations. But specifically inclination and eccentricity change on timescales that are slow enough to matter when you zoom out that far.
Thank you so much. And again, great presentation. Tough to do remote, and you did a great job. Thank you so much for joining us. All right, next we would like to welcome Julia Fancher on tidal disruptions. Welcome, Julia.
Hi, everybody. My name is Julia Fancher. I am a senior at Syracuse University studying physics and applied mathematics, and I do high-energy astrophysics research with Dr. Eric Coughlin. Specifically, I research something called a tidal disruption event, or a TDE. And so to start off, of course, we have to know what is a TDE. So a TDE occurs when a star gets so close to a supermassive black hole that the gravity of the black hole overcomes the star's self-gravity and rips it apart, just like that. About half of that debris is bound to the black hole, which means it's going to orbit and eventually fall back onto the black hole. This fallback process releases a ton of energy as light, so what we see is we get a light curve that looks something like that. If we can predict what kind of star and what kind of black hole would produce a light curve like this, then we have a really good window into the stellar populations in black holes and distant galaxies, which is pretty cool in my opinion. One way we have to model a TDE is to use a numerical simulation, which, as we just heard, is pretty accurate, but can be incredibly computationally expensive and very time-consuming. So if we can, we'd much rather use an analytical or mathematical model, but those mathematical models make a lot of assumptions, and sometimes those assumptions aren't accurate. So what I've been doing for the past couple of years is using numerical simulations to test analytical models and seeing if we can use those to be more accurate, more efficient, and interpret TDEs accurately. So when I'm using models, when I'm testing them, I'm looking at the fallback rate, and specifically I'm looking at the peak, so this point right here. So I'm going to talk about the time to the peak and the magnitude of the peak when I'm talking about the peaks of fallback rate. So in all the TDs that we've seen thus far, we have a very tight time constraint, about 20 to 50 days, and a very wide constraint on the magnitude. So that covers multiple different orders of magnitude, so there's a pretty big range there as well. If we have an accurate model, we should see things that echo this, so very tight time constraint, very wide range of peak magnitudes. So we have a couple different models. First one that's been around the longest, it's the standard. It's called the frozen-in model. And this model says that when you get close enough to the black hole, the gravity of the black hole is so strong that you can ignore the pressure and self-gravity in the star. When you ignore that, you can predict anything you want about a TDE by just knowing the mass and the radius of the star and the mass of the black hole. So anything you want from just 3 parameters, which is pretty nice, but unfortunately, if you were here last year, I talked a lot about this model, and my conclusion was this model kind of sucks. So we have a newer model called the maximum gravity, or the MG model, which makes actually very similar assumptions to the frozen approximation, but there's some mathematical changes that I'll spare you the details of. Basically, it includes self-gravity in greater detail. And so you know a lot more about the stellar structure, you know the density profile and things like that. So the pictures we get from both of these models are right here. This is kind of a crazy plot, I know, but the big thing here is across the bottom, those horizontal-ish lines, that's the frozen approximation predictions. So the 3 different lines are 3 different ages, going from youngest at the top, oldest at the bottom, and the different colors are different masses. You can see right away here, the timescales have a huge range, so again, another indication that this is not a very good model. What we are looking for is something like these 3 lines up here in the corner. That is the MG model predictions, so I'm going to zoom in for those. So now we have a timescale of about 20 days of all of our peaks, which is pretty good, and we have a pretty wide range of magnitudes, which is also something we're looking for. So I ran simulations to test every single one of these points on this plot, but I'm only going to talk about the youngest stars, so the ones all the way on the left over there, for the sake of time. The youngest stars are the most abundant in the universe. They're disproportionately seen in TDEs, so talking about the youngest stars is a pretty good way to talk about all of TDEs. When I run a simulation, I get something that looks like this. This is a fallback rate. That inset there is a zoom in on the peak. So the star is the prediction from the MG model, and the inverted triangle is the peak from the simulation. So they match pretty well right there. And then those vertical lines on either side give us a 95% interval. So where the fallback rate is at least 95% of the peak, this is kind of a way to make sure that if we have any numerical noise, we're still accounting for that. We're probably somewhere in that time range. So I did this 24 times for all the different ages, or sorry, all the different masses, and I get something that looks like this. So again, here we have the stars are the predictions. The triangles are the peaks from simulation, and then this time the 95% interval is the error bars. This is absolutely remarkable. It's pretty hard to overstate how good the NG model is at predicting this. This is absolutely fantastic. So as we just heard, the Very Rubin Observatory came online this year. It's seeing a lot of things like asteroids, but also seeing lots of candidates for TDEs. And now we have a way to quickly, accurately, effectively model TDEs, figure out stuff about the cellular populations of black holes, which is super awesome. I have written these results in greater detail in a paper. It's been accepted, but it's not officially out yet. The preprint is there on the QR code if you guys are interested in learning more about that. I'd like to say thank you to my co-authors and also my mentors right here on the bottom. And then thank you to the Astronaut Scholarship Foundation, of course, and thank you to all of you for listening. If you guys have any questions, I'd be happy to answer them.
Wow, thank you, Julia. Who has a question for Julia? Oh, there has to be one. There it is.
Hey, Julia, great talk. I noticed at the start you said like these release a lot of light, and then the y-axis of the graph was at 10 to the 44.
Yes.
I'm not familiar with like what that unit is. Is there like perspective on like what?
So they're in ergs, which is kind of an astrophysics thing. It's actually a lot smaller than a joule. Weirdly, they like to kind of do it, but 10 to the 44 is massive. Like our sun is probably, I think, somewhere in like the 10 to the 30-ish range. So this is quite right here.
Okay, thank you.
I'm just going to say wow, because I have no idea what y'all just said. But, oh, wow. Wow. Julia, thank you so much. That was great. Well done. Well done. Next, let's welcome Grace Gratton, characterizing solar sources. Welcome, Grace.
All right. Hello, everyone. So I'm Grace Gratton. I'm a rising junior at Embry-Riddle Aeronautical University studying space physics. And today I'm going to be talking to you guys about how I characterized the mesoscale solar wind. You can think of that as like the medium scale, and why it's so important to characterize this to take a first step in being able to forecast when it's going to affect our assets in space. So this talk's going to be broken down into 3 sections. First, we're going to talk about the solar wind and why it's so important to study. Next, how I characterize the mesoscale solar wind. And finally, what that characterization means. So the sun's corona is a halo of extremely hot plasma. It's so hot, in fact, that this plasma escapes the sun at supersonic speeds, creating the solar wind. This outflow of charged particles and magnetic fields is constantly bombarding Earth, disrupting satellites and other spacecraft that we rely upon. This can have really detrimental effects. 3 years ago, a solar storm increased the atmospheric drag on satellites, causing them to fall and burn up in Earth's atmosphere. Did anyone get to see some northern lights last summer? Nice. So if you saw a spring storm, that storm actually forced all of these airplanes to move further south because of the threat of communication and navigation losses. These are typically caused by the largest scale of the solar wind, coronal mass ejections, or CMEs. But between CMEs and the largest scale of the solar wind lies the ambient solar wind. And that ambient solar wind is permeated by mesoscale structures. These structures are massive. They are always larger than the Earth's protective magnetic field, making them a very significant threat to us. We can think of CMEs as a hurricane, and if the CMEs is a hurricane, then this mesoscale solar wind is going to be the everyday thunderstorm. Not as destructive, but still extremely important. Because they're so dangerous, it's very important to forecast these, and that brings us to my project goal, to characterize the mesoscale solar wind so we can eventually predict when and how it's going to impact the Earth. Now we're going to talk about how this was achieved. First, we collected a series of events when mesoscale solar wind was geoeffective, meaning that it impacted the Earth. We used events when X-ray signatures from radiation belt depletion exhibited periodicities that matched those detected in solar wind density fluctuations. Using this event list, we were able to trace it all the way back to the ACE spacecraft to get its properties like solar wind speed and composition. Finally, using a model, we traced it all the way back to the sun to determine where it came from on the sun.
Overall, we characterized 118 different events into 4 different solar source regions and 4 different solar wind properties. I'm only going to talk about one of each today, but if you're wondering about the other 6, I would be happy to talk about it afterwards. So we're going to begin with a source region example. This histogram here shows the distance that each event was away from a coronal hole, which is where the open-closed boundary is. The y-axis is going to show the number of events, and the x-axis shows it's sorted into bins of 1 degree from a coronal hole boundary. More than 80% of these events originated from within 3 degrees of the magnetic open-closed boundary. That's really fascinating. Next, we're going to have a solar wind property histogram. This graph here shows the solar wind speed. Again, on the y-axis, we have the number of events, and on the x-axis, we have the solar wind speed sorted into bins of 100 kilometers per second. Now, it might look like the solar wind is really fast across this graph, but we're looking at mostly slow solar wind, which is less than 500 kilometers per second. Nearly 90% of these events were driven by the slow solar wind, which is known to form at the magnetic open-closed boundary. Our other 6 results also echo this similar theme, that the geoeffective mesoscale solar wind commonly originates from the magnetic open-closed boundary. That boundary can be seen here in green. It's where closed fields that loop back to the sun meet open fields that extend out into interplanetary space, allowing for really hot, dense plasma to be released. This was actually the hypothesis that we had for this work, and this characterization confirmed it. This is actually the first time that we've ever been able to link this many events to their source regions at the sun. And in the future, we want to characterize more types of mesoscale solar wind. That way we can protect some of our assets here on space and our spacecraft and astronauts as we venture beyond. Finally, I want to close with thanking the Astronaut Scholarship Foundation and my advisor, Dr. Samantha Wallace, who is here if you want to ask the queen of the research herself. All right, are there any questions?
Thank you so much. Love that your professor's here. That's awesome. Who's got a question for Grace?
That was really, really cool. Great presentation. So I was wondering, you talked about the slowest speeds that the particles were, that the solar wind was moving at, and then you talked about some of the effects on Earth, that we were seeing. Are these events something that we're able to predict and be proactive on, or are we reacting to events like this?
So these are events that we're able to predict. We're really good at predicting the largest scale, those coronal mass ejections that I mentioned before. But that's something that we've really focused on because they're so significant, they have such big impacts. But we're learning that the smaller scales, like the mesoscale, can also have really big impacts, and that's what this work is trying to begin being able to forecast when those events are going to happen. That way we can detect it and be prepared for it. Yeah.
Wow, cool. Solar winds. I love it. Isn't that a Frank Sinatra? No, that's a different song. All right. Grace, that was fantastic. We thank you so much.
Thank you.
All right, next we're going to welcome Logan Hansler and talk about scalable cryogenic LED mapping. Welcome, Logan.
Hi everyone, my name is Logan Hansler. I'm a senior at the University of Chicago. I study molecular engineering and astrophysics. I'm really excited to tell you all about my work in developing an LED mapping platform for the next generation camera for the South Pole Telescope. So in order to tell you about this, I need to take you back to the beginning. And I mean all the way to the beginning. So the Big Bang happened, and after, the universe is this hot, dense mass of subatomic particles, and there's thermal radiation that's trapped there, ricocheting off of these particles, that it is simply too dense and too hot for them to be able to escape, until eventually we get to the recombination event, when we get the emergence of the first neutral hydrogen and helium, and now the universe is transparent to that radiation. So that is emitted, and that still exists today in the form of the cosmic microwave background radiation. That is then affected by later things such as the reionization, when we have the emergence of the first stars, and the growth of galaxies and clusters that came afterwards. Those exist as secondary signals in the cosmic microwave background. The South Pole Telescope seeks to measure that cosmic microwave background, and it's currently equipped with the SPT 3G camera that lives there. But there is currently work going on to upgrade that to the SPT-3G Plus camera that really will measure the cosmic microwave background with unprecedented precision. And so it seeks to measure those secondary effects to then backpropagate that and see if we can understand the early universe to see its overall structure and then extrapolate that to understand why things exist the way they do now, maybe discover some new physics along the way. So the camera is powered by these detectors that are microwave kinetic inductance detectors, or MKIDs. So this image that you're seeing is actually two MKIDs. So it's made up of this element, that's the inductor, and a capacitor. And there's another inductor and capacitor pair over here. So that forms an LC circuit that has a characteristic resonant frequency. And when a photon is incident on this circuit, it heats up. These are superconducting detectors, so they're at very cold temperatures. When it heats up in response to that photon, we can see a shift in the resonant frequency. And by measuring that shift, we can then see that effectively across a large number of detectors, we can use that to map out an image of the cosmic microwave background. But the issue there is that, well, really the benefit of doing so is that these detectors, we can get a large number of them hooked up to a single read line. Like SPT-3G Plus plans to use 31,000 of these with 800 on an individual read line, which is very good for getting really high precision images. But the problem then is that if these resonant frequencies wander and they collide into one another, then we have problems reading them out. Because if we see a certain resonant frequency move, and that actually corresponds to two detectors, then we can't trace back which detector had the incident photon. So that's where the idea of LED mapping comes in. So if we can use LEDs positioned over an array of these MKIDs and use that to essentially figure out which frequencies correspond to those detectors, then we would be able to go through and do a following round of fabrication to separate out those frequencies and make sure that we can improve the yield. And these stars show potential locations where we could put LEDs over this. Effectively, with one LED, we would want to hit 3 of these hexagons that effectively hits 6 different MKIDs. And a waveguide would filter that out from being able to affect the other MKIDs in a significant manner. And so these 6 that are very close together are separated out enough in frequency that we don't think that that would really, that they would interfere with one another in a significant manner. So this allows us to effectively understand where those frequencies are, and then we can tune them. So an example of what the output would look like when we're testing is this. This is one of the successful results that I got where, oops. You can see the dark signal here, and when the LED is turned on, you can see it shift. So it goes sort of up and to the left where it's flattened and the resonant frequency shifts. So that's a really good response to the LED being turned on. We can see that is conserved even when on a later day, the resonant frequency has shifted to a different spot just because of the changing conditions in the cryogenic fridge. And the important part is that that shifts relative to where it is when the LED is off, not necessarily that it's shifted with the frequency, so that effectively allows us to read out that detector. So that was done using this LED array controller that I had designed that lets us control up to 160 individual LEDs. And it can be daisy-chained based off of these connectors here to potentially control more if necessary. That is really useful because we would have an array like this to test the full SPT-3G Plus wafer with all of those detectors. This in particular has 140 LEDs, and that follows the current design, but as that design is iterated over, it's possible that that will need to be updated, but this is resilient enough that we should be able to still use that same software and hardware architecture that I developed for it. That particular board that I showed you would be implemented in this box design that I'll skip over a little bit in the interest of time, but I'd be happy to talk about after the presentation if anybody's interested, where the wafer is effectively placed here with the waveguides that I mentioned, filtering out the light, and the board is placed on top. So in conclusion, that hardware and software that I developed allows us to quickly and effectively and reproducibly map out those resonant frequencies corresponding to the physical locations of the LEDs on the wafer, which would then allow us to go through that following round of fabrication, improve detector yield, and actually hopefully use this camera on the South Pole Telescope to discover some new science. So I would like to thank Professor Benson, Dr. Natoli, and Professor Karlstrom, as well as the UChicago South Pole Telescope Group and the broader SPT-3G Plus collaboration for allowing me to work on this awesome project, as well as the Astronaut Scholarship Foundation for giving us all the once-in-a-lifetime opportunity to meet each other in the 2025 cohort and all the amazing people that are here as well. So thank you very much. I'd be happy to take your questions.
Thank you. Let's have one question for Logan.
All right. It was a lovely presentation. First off, I would say that I'd be flattered if you decided to use green ones in the future. But I was curious, an actual question, I was curious if the detectors have different sensitivity to different wavelengths of light and if you chose a specific color of your LEDs based off of this.
So they definitely do have a specific sensitivity based off that light, but in general, they are just really, really sensitive. These are at superconducting, like they're superconducting circuits at very low temperatures, so any incident photon would really generate a response, or almost any. So ultimately, they're going to be employed with, millimeter and submillimeter waves, because that's the purpose of what the telescope's actually trying to measure. But for testing, we actually do use green LEDs. That happens to generate the right response. Really, I don't think that it would be a problem if we used red or blue LEDs. Effectively, we just need to be able to see that response due to that photon incident, and any given LED would really do the job for us.
All right, thank you so much. Oh, yeah, go for it. We'll make time.
Yeah, great presentation. I was just curious, this is all, you're doing your testing in Chicago prior to installation of the modules?
Yes, all of this testing is happening in the laboratory. There's a cryogenic fridge where we put the detectors in, and we put that LED array in as well. We control that from, the LED array controller sits outside that cryogenic fridge, and all of it is tested in there in the same environment that it effectively would be when it's deployed, but not integrated into the full detector plane, just an individual unit, so that we can test that part of it, so that can later be, fully tuned and then assembled.
Great, thank you so much, Logan. Next, we would like to welcome Erica Sundermeyer on disk formation. Welcome, Erica.
Hello. My name is Erica Sundermeyer. I'm here from the University of Rochester in New York. And today I'm going to tell you a little bit about the formation of solar systems and how specifically the last 5 years of observations are changing radically how we think about the formation of planets. Very exciting stuff. So let's get straight to it. How do you build a solar system? We start with a large round cloud of gas and dust in space, which will collapse under its own weight. And at the center of that collapse, you've got a protostar. It's not a star yet, but it's on its way. And you have a bunch of infalling gas called the envelope. And it's all going to be kind of rotating a little bit, so you're going to get a swirling disk around the protostar. And later on, as the protostar kind of eats up all of the surrounding gas, that disk is going to start to clump up and form rings, and those rings will be the birthplace of planets later on. So, of course, at the last stage, we have a lovely solar system, the kind that you're all familiar with. But there is a critical error with this model, which is right here. So I'm going to ask you all a question really quick. I want you to really tap in your memory here. Have you ever seen a spherical cloud before? Yeah, okay, me neither. So this is what our data looks like, and there's not much round about it at all. But this is a system that I study. It's called PER-M2. It's a protostar in the Perseus molecular cloud, and it is a very young system with a very massive disk. How does this disk get so big so early? That's because of this, sorry, I'm shaking a little bit, but that green structure there, which we call a streamer. So for a sense of scale, that disk is about 3 solar systems across, of our solar systems. That streamer is about 300 solar systems long, and what it's doing is it's connecting the outer envelope and bringing in all of that gas, directly dumping it onto the disk. That's going to mess up our disk. This streamer exists exactly because of the asymmetries that spherical cloud model ignores. But not only do streamers transport mass, but they transport angular momentum, which is to say that they're bringing in rotation from these large to small scales. Mass and rotation, that's our disk ingredients. The disk is where the planets form. So we really want to understand how this rotation is changing from large to small scales, because that's going to eventually, at the end of the day, determine how big our disk can be, where the planets end up forming, again, all the initial conditions for that kind of thing. So how do we study a streamer. It's weird. The shape changes depending on the system. It's confusing. No one's ever done this before. So what I've done is I take my streamer data and I kind of ball it up and I throw it against the wall and see where the splatter is and decide which region I want to use. So we're plotting here on the right angular momentum as a function of distance away from the center object. And you'll see that answer kind of changes depending on which region that we're using. So the colors correspond to these 4 bits of data. But they all seem to kind of follow like a broken power law kind of behavior. This is a log plot, so a straight line is exponential growth or decay. So the answer is kind of different, but they all show that kind of broken power law behavior, which we do expect because we expect to see streamer material. Again, it's from outer gas cloud and it's coming into the disk. So that flattening out, the change in the power law is indicative of streamer material starting to kind of become part of the disk. So that kind of makes sense. But we want to understand how this is different from what we were doing before, right? So what's changed? The good news is we don't have to abandon all sense of symmetry entirely because the envelope material is still kind of doing like a spherical, rotating, well-behaved thing. That envelope material is the light bit here, and that streamer is going to be that contour in this plot. And the envelope material is this blue, and the streamer is that red pie slice from before. And what we're seeing when we put them together, again, angular momentum is a function of distance, is that they look quite different. So the envelope material is kind of, again, kind of smooth and round and spherical, and it's following kind of a single law, or single power law behavior, which at the end of the day is just quite different from what the streamer is doing. The streamer does have kind of a envelope to disk transition to it. Great. So where do we go from here? Basically, we've seen streamers. They're asymmetric. They're born from asymmetries, and they're changing everything that we thought about before. They're bringing in mass and angular momentum, changing our disk properties, and we're seeing that you can't study planet formation and disk formation without studying star formation at the same time. We're seeing that solar systems don't form in neat, discrete steps. They're forming all at once. And again, all of the solar system fun facts are their origin is way earlier than we thought they were. So thank you to my mentor from U of R, Dr. Segura Cox. She's been amazing. Thank you, ASF, and thank you all for listening.
Thank you. Who has a question for Erica?
Hi, I'm wondering if there's any way you can predict like the critical radius at which the power law kind of shifts, because it seems like there's like at lower radiuses the power law is pretty similar and so I just like wondering if there's a way you can predict or calculate that critical radius.
Well, there is literature about that. The problem is individual systems are very hard to compare to one another. It's like they're all kind of their own special snowflakes, and they're all very chaotic. So it's hard to predict. So you would think of doing like a statistical study with a lot of systems at once. That's kind of tough because every system's going to be very different. So it is kind of difficult. But that kind of when we do see like streamer material becoming entirely like part of a disk, when that power law kind of completely flattens out. Again, we're hoping to get better resolution in the future, but that will tell us where the disk boundary is, which is again like at early stages hard to define. But so to answer your question, like it's tough, basically. Yeah.
That makes sense. Thank you.
Okay. Thank you so much. Thank you, Erica. The only thing I've ever thrown against the wall to see if it's done is spaghetti. All right, and on that note, let's talk about the largest known exoplanet with Gavin Wang. Welcome, Gavin.
Hi, everyone. I'm Gavin Wang. I'm a rising senior at Johns Hopkins University, studying physics. Today I'll be talking about my project measuring the mass and radius of the largest known extrasolar planet. So Erica just gave a great talk about how to form a solar system, and I'll be talking about the end products, like the exoplanets themselves. So a great question to ask is, why study them in the first place? To me, it's two reasons. The first is to learn more about ourselves. So we obviously live on planet Earth, but there are still some questions about how the solar system, how the Earth formed, and how life emerged on Earth. Second is to define our relation to the rest of the universe. So currently, Earth is the only planet known to host life, but there might be other planets that are habitable or host life. So I think studying exoplanets can answer the question of, are we unique and very lucky to be here, or are we just one of many civilizations? So we've made a lot of progress considering that the first exoplanet was found just 30 years ago. Now we know of nearly 6,000, and as you can see here, they span many orders of magnitude in their properties. They have very different masses and very different orbital periods. So there's a lot of diversity in this population, and one of the big questions right now is understanding how did this diversity come to be. And one way towards answering that is to look at extreme cases, so the planets that are in between populations or on the edges of the distribution. And in this plot, you'll notice that a lot of the points are purple, which means that these planets were discovered via the transit method. And what that is essentially we look at a planet, and as it passes in front of its host star, it will block some of the light from the star, so we observe that the star gets dimmer for some period of time here. And this occurs periodically once each time the planet orbits around the star, and we can measure that. It gives us a lot of useful information about the planet. And we did that. We used data from the Transiting Exoplanet Survey Satellite, which is an ongoing mission that monitors the brightness of stars across the whole sky. So it also observed our target, which is HAP-P67, and we see these transits here. So I folded many transits on top of each other to get a higher signal-to-noise ratio, and the key property that we can get from this data is the size of the planet. So it turns out that this planet is really big, 2.14 times that of Jupiter, and this is the largest one that's ever been found so far. Another important property of planets is their mass. So this can tell us what they're made of, and we measure their masses by a technique called radial velocities. So typically we think of a planet as orbiting around a star, but in reality they're orbiting each other they're orbiting around the common center of mass. So the planet, which is much lighter, it makes this big orbit, but the star is also making a small orbit, and it wobbles. So by measuring this wobble, we can essentially weigh the planet. And we measure this wobble by looking at its spectra and the Doppler shift that moves the spectrum around in a wavelength. So we also did exactly that. Plotted here are the radial velocities, and I've plotted it phased to the orbital period of the planet. So you can see that the data follows roughly like a sine curve, which is what we expect from a circular orbit. And this is data from the Keck telescope in Hawaii, as well as new data we got from the Wind telescope in Arizona. And you might notice that there is a lot of scatter in the data. That's due to stellar activity, which I can get more into if anyone's interested. But the main thing that we can measure is the amplitude of this sine curve. That tells us that the planet is 0.45 plus or minus 0.15 Jupiter masses. And with the mass and the radius, we can calculate the density of the planet. It's 0.06 plus or minus 0.02 grams per centimeter cubed. And to put that into context, that's roughly the density of cotton candy. So this is very low density for a planet, and we think that this is due to stellar radiation, which a lot of it heats up the planet, and that causes it to puff up. And recent other works have found the planet has like a comet-like tail, which is consistent with this low density. It means it's losing its atmosphere because it can't hold on to it. So some takeaways: studying extreme planets can teach us about planet formation and more so in this case, planet evolution. Our planet is the largest and third least dense planet out of nearly 6,000, and increased stellar radiation inflated the planet. Some future work is to study the planetary tail to better understand the mechanisms of atmospheric escape. Thank you to my mentors, Nestor Espinoza, David Singh, and many others. And thank you, ASF, for giving me the opportunity to be here and present. Thank you.
Oh, thank you so much. Question for Gavin. One towards the back.
Thank you for that talk. That was great. Speaking about your radial velocity method, given the scatter in the data, can you speak to your confidence in those parameters that you derived?
So the mass and the other orbital parameters?
Yeah, like you're fitting to the sine curve, how confident you are in that.
Okay, yeah, great question. So the main difficulty is dealing with like the noise, the scatter, and we use some methods. One, just like ignore it and fit and see what we get. Another is to use like Gaussian processes, which is a sort of non-parametric method that can fit for like random noise. And we do both methods, we compare them, and they give similar results. So the uncertainty that I reported is pretty big, and so it's like a conservative estimate. So I think it does capture like the true value.
Thank you.
Thank you.
Thank you so much, Gavin. Next, we'd like to welcome Matthew Wanta on optimizing drone search paths. Welcome, Matthew.
All right, good morning. My name is Matthew Wanta. I'm a cadet at the United States Military Academy at West Point, and I'm a math and computer science double major. So as Boston already talked about earlier this morning, drones have become increasingly prevalent on the modern battlefield, and also like Boston, you guys get in the unclass version. So UAS have limited flight times due to a series of physical constraints. These are battery life, weather, and even payload weight. And that means they don't have a lot of time in the sky. So we need to make every second they do have count. That's why my research works on optimizing these search patterns to make more efficient target location. Because modern search approaches are insufficient to the task. Now, a lot of these, such as the expanding spiral, as you can see on the screen to your right, start with the drone in the center and moving outward in a series of concentric rings. These are rigid geometric patterns that were actually developed back in World War II by maritime search operations. Mainly for submarine hunting, these took place over a flat and more or less featureless ocean. So it's mathematically optimal for those domains, but not for the chaotic environments of the modern battlefield. So my research is able to integrate terrain and irregular search domains through a method called a particle filter. A particle filter, what we do is we take our search space and we seed it randomly with a series of particles with a given size and position. And the greater the size of the particle, the greater our belief that the target is there. And as this is a probability field, the sum of those particles' weights must be 1. So here you can see an example of one such particle filter. The black dots are our particles, and the blue is that drone's field of view. Let's see it in action. And the red is a trace of the path as the drone moves across the simulation. You can see that the drone observes those particles, and upon not finding the target there, reduces the weight of those particles. But as it's a probability field, the weight of those particles must be displaced elsewhere in the model. Hence, you can see some are regrowing and some are getting smaller. So that's the expanding spiral. Let's try a more novel steering mechanism. So I propose the artificial potential field. And if you look at that equation, squint hard enough, you'll probably see a Newton's law of gravitation in there. And that's because it is. So the drone is getting pulled on each particle with a strength proportional to its weight and inversely proportional to its distance squared. Now, we ran this with on our theoretical search domains, and all we got was just a crappier version of the expanding spiral. So now let's add terrain. So we can see different terrain types, water, forests, roads, etc., with different relative weights to result in a more informed search. And depending on what we're looking for, we can tailor these relative weights. For instance, if we're trying to find a vehicle, it's much more likely to be on a road than in the middle of a lake. We're able to build on pre-existing satellite segmentation research to go from a raw satellite image, extracting terrain classifications, and then using that to seed our filter. So let's see that in action. So you can see here our drone autonomously follows and traces roads and doesn't waste a lot of time going over that lake in the center. So this results in a much more intelligent path than a simple expanding spiral. But while we intuit that that's better, how do we quantify that? Well, we have two main performance metrics, and we'll focus on the second one of those, which is the area above the curve, which gives us an indication of how long it will take for us on average to find the target. When we compare the artificial potential field to two canonical search patterns, which are the horizontal sweep and expanding spiral, think of the horizontal sweep as like how you'd mow your lawn, just going back and forth. Our artificial potential field greatly outperforms the expanding spiral and horizontal sweep on around a series of around 100 of these satellite images. And it's significantly faster. So a lot of further work is required in understanding the entry metric and also evaluating different strategies. And also we're partnering with Lincoln Labs to get some hardware to do some actual field tests. I'd like to thank the Math Sciences Department at West Point, also my advisors, Colonel Blumen, Dr. Steckerreiter, and Dr. Dorda, as well as the SOCOM Ignite program, the ASF, and of course, the American taxpayer. Thank you.
Thank you. Thank you. Who has a question for Matthew?
So when you place those dots of like the different sizes based on like the statistical probability that that's the target, is that going to remain like a human input, or is there some sort of algorithm to place those points for you?
Yes, it's just a random uniform distribution.
Okay.
With that short answer, we can have one more question.
Hey, so in the simulation that you showed where you were traveling around the lake, what was the actual goal of the drone?
Yeah, so the drone's trying to find a target, like a vehicle that would be in the simulation area. The target isn't actually, sorry.
Gotcha. So the weights are related to, like, for example, roads are weighted more heavily because that's more likely for them to find the target there.
Exactly.
Okay, gotcha.
Thank you.
All right. Thank you so much, Matthew. Next, we would like to welcome Keanu Brayman on Space-Rated Robotic Arm. Welcome, Keanu.
All right, hey everyone, I'm Keanu Brayman. I am a student at the University of Central Florida studying mechanical engineering, and today I'll be presenting work that I performed over the summer at NASA Marshall Space Flight Center in Huntsville, Alabama, or as some of you may know it, Rocket City. So I'll start us off with some background. NASA's Artemis program is seeking to not only return American astronauts to the moon, but to establish a sustained presence of humans on the lunar surface. And that requires a lot of things, a lot of new technologies, and one important piece of that will be a base on the lunar surface, or as my mentor would say, building some moon houses. A key way to do that is using something called in situ resource utilization, or ISRU. That means using locally available resources in your environment to construct, to build things rather than launching things from Earth at high cost. And a resource that is abundantly available on the moon is lunar regolith, or lunar dust, moon rocks basically, the stuff that's on the surface. And the last thing I'll mention is, so I worked with the Materials and Processes group at Marshall, and they recently had a breakthrough where they were able to create solid, structurally sound parts at a small scale using just simulated lunar regolith without any additives or binders in a powder bed fusion machine. So that brings me to the goal of my work that I supported, which is to take that to a larger scale. So the parts that they made were maybe about this large, no more than a couple centimeters across. The parts that we want to make are larger, eventually enough to build actual surface infrastructure. So we wanted to build a directed energy deposition system that would consist of a robotic arm. You can see that right there. That was my main part of the project. Also a high power laser, we'll get back to that, and a regolith conveyance system. This used a vibratory motor to actually feed powder into our laser spot. And I want to mention, so the laser, I have this laser pointer here. This is probably about 5 milliwatts or something like that. Our laser is up to 1,000 watts, so about 200,000 times more powerful than this thing here. Just thought that was neat. So I'll briefly talk about the X-Link robotic arm. This was the main thing that I worked on. It was provided to us by a company called Motive Space Systems. They also made the arm on Perseverance. They designed it to be capable of operating in vacuum and resistant to lunar dust, which is very abrasive. It was programmed using ROS2 and Python. I did a whole bunch of simulation and toolpathing. I won't get too much into that. Feel free to ask me later if you're interested. So the cool thing, I think, that I'll talk about more is integration and testing. So let's see, over on the left here, you can see our integrated system with the robotic arm, our laser, and that yellow wire there is our laser fiber, routing our laser light in from outside the vacuum chamber. In the middle here, you can see the vacuum chamber itself, the V20 chamber at Marshall. It's, if I remember correctly, 20 by 36 feet. It's quite large, so it was really cool to get to go in there and have space for our setup. And then on the right here, you can see the regolith conveyance system, so that has a hopper on the top right there filled with simulated moon dust that would then feed with the vibratory motor through a tube and down onto our build plate. But enough of me rambling about this system. Why don't I just show it to you in action? So here we have the robotic arm moving into position. We start powder flow, and there's our laser. The only thing that annoys me with this video is that there's no really cool laser sound, but because we're doing this under high vacuum, it's basically like it's in space, and there's no sound in space, so this is all we get. We just get a cool visual there. And that brings me to results. So there's a lot of material characterization work that's ongoing at Marshall, looking at the material science side of this, but I can show you the samples we have so far. So for reference, these are about 2 inches wide or 1 to 2 inches tall, so they're still small, but a lot bigger than what we could make on a powder bed fusion machine, and we could have also made these a lot larger, so the potential for that is there. So over on this side, we have atmospheric parts, so we made these in the vacuum chamber, but without being pumped down to vacuum, so these were the first parts we made where we already saw really great success. On the bottom part here, I want to mention we actually did a restart and rework study where we built that bottom section here. Then we stopped the print, we came back and did sort of a repair type of operation and added more material on top here, something that's never been demonstrated with lunar regolith in this type of system. And then over on the right here, we have parts that we actually made under high vacuum. They were extremely structurally sound. They have a nice glassy interior. They are hard to break apart, did not just come off the build plate, so they show extreme promise. So getting into the conclusion of this work and what's next, I was able to just show you all that we created multi-layer thin wall structures, which is an extremely promising first step here. Future work, it will involve improving my toolpathing code, which I actually did already before leaving my internship, to be capable of making bricks, and even something that will be worked on is to make more complicated things like cylinders and domes, eventually moving to the sorts of structures you would need for something like a moon base or launch pads, towers, whatever infrastructure you need. And this has huge implications not only for lunar exploration, but potentially one day even the exploration of Mars. I'd like to acknowledge my amazing mentor, Parker Sheikh, as well as Jim Lydon, who's not on here, my great team members, Caleb and Tanner. I want to thank NASA Marshall Space Flight Center, the NASA Pathways program, and I'd like to thank everyone at the University of Central Florida, my school that nominated me, especially my research advisor, Dr. El Gohari, who's here today. And I want to give a huge thank you to the Astronaut Scholarship Foundation for giving me the opportunity to be here and share all this wonderful work with you guys. Thank you.
Thank you. I'm doing air quotes and saying laser right now, if anybody remembers Dr. Evil.
But we did that a lot on our project.
Yeah, I bet you do. I had to go there, sorry. Who's got a question for Keanu?
I got a quick question real quick. How does the material properties of your lasered regolith compare to material properties of things that we have here on Earth, like concrete or other building materials?
Yeah, so that's a great question. Like I said, material science isn't as much my field, but I can say that on those initial samples I showed that were built in a powder bed fusion machine, my team did some structural testing. They did a compression test, and they found results several times, like I think 3 or more times the compression strength of typical concrete. So In compression, they are extremely strong. Tension, not as much so, but compression is the more important metric, and we're working on improving tension as well. We're also looking at things like heat treatment to improve those structural properties. It's basically a glass ceramic, if you're familiar with that, so that should tell you, but if you're more familiar with that material science. But so they have really great properties, similar to concrete, and they have huge promise for structural applications.
One more question for Keanu.
I just had a quick question. So I saw you use LHS1, which is from the Highlands region. Do you know if this will still work for the lunar mare regions, or if there's limitations based on like the iron content or something the way with the glass forms?
Yeah, there's definitely a lot of differences in the different simulants, and we did use LHS1. We have not yet done tests with mare simulant, although that's certainly something we intend to do. We also want to look at even things like Martian simulant. There will definitely be differences in the material, but a big thing that's key to this is thermal management. So how we do different passes of the laser and our deposition to allow the material to crystallize and form into those structures, and so we can potentially adapt depending on what material composition we have. Something we also noticed that was interesting in our powder feed system, we saw material separation where different colored particles, so different materials would sort of separate out, which we were worried that would impact our material process, but we actually still got really good results. So this is something that definitely can work even if the material composition is a little bit different, so different Highlands versus mare simulant. There's definitely a good chance those will work, and that is something we will try out.
Thank you so much. Thank you, Keanu.
Thank you.
We would now like to welcome Thomas O'Keefe, biologically plausible SNN-based path finding. Welcome, Thomas.
All right. Hello, my name is Thomas O'Keefe. I attend Drexel University. I'm studying computer engineering, currently working in Drexel's DISCO laboratory. We're a big fan of long acronyms at Drexel. And today I'll be talking to you about prototyping neuromorphic path planning hardware, which I think dovetails very nicely with all of the drone presentations that we've seen so far, because a lot of the major applications of this technology are, in fact, in drones. So, to start off, what is flexible path planning? Well, a lot of mammals, humans, rats, all other kinds, exhibit two very important behaviors. The first of these being neural preplay, which is sort of the ability to visualize where you're going, and VTE, vicarious trial and error, which is the concept by which when you are presented with uncertainty, how do you sort of deliberate? How do you pick a path? And we can observe both of these in rodents using electrodes, and this has also been theorized about as far back as the 1940s. So we can see this nice plot here. On the left we have VTE stage 1, and you can sort of see it's thinking about the left, thinking about the right, and the path is sort of circuitous. And then by the time you decide on a path, you more or less know where you're going, so you don't see neuron activation along other paths. So spiking neural networks are sort of the way that we can implement these algorithms. It is a type of traditional artificial neural network where you introduce sort of a time dimension, and it becomes a dynamical system, for those of you that are familiar with the physics behind that. I'm not so much familiar with that. But you can see the sort of model of a neuron here is you get a bunch of inputs, you accumulate them, and once you have a large enough accumulation of inputs, you create your own output, which then becomes the inputs to neurons that are further on down the chain. So we use a local, biologically plausible learning rule called eligibility propagation, which essentially allows us to cause these neurons to learn the proper delay between presynaptic neurons and postsynaptic neurons, which is basically when you fire, receiver, and transmitter. And the key part of this is that traditional algorithms like backpropagation just are not biologically plausible. They can't really be what your brain is doing because you either need information from the future or you need too much information. So this allows us to realize this computation in real-time hardware. So here we have some nice pretty graphs, courtesy of John Hopfield, who is a recent Nobel Prize winner. This is from a study in 2013. And we can see spikes propagate outwards from the cyan, where's the laser? Yeah, the cyan origin, and the red dots indicate the spike wave as it propagates outwards. And all the way on the right here, we can see plots of neuron excitability, which is just sort of the idea that when you spike, you're not allowed to spike for a certain amount of time after that. So you are less excitable immediately after you spike, and this wave sort of propagates outwards in space through time. So what is my contribution to this research? Well, I am an FPGA engineer by trade currently. FPGAs, or field programmable gate arrays, are sort of a more flexible CPU, also more flexible than an ASIC as well. There are a certain number of design trade-offs, sort of you could see here. Somewhat better than an ASIC in terms of cost and time to design the actual hardware, but sort of better than a CPU in the sense that it is faster, more parallel, and capable of exploiting some of the inherent parallelism in these SNN algorithms, because you can calculate the state of each neuron simultaneously, completely at the same time. You don't have to worry about things like CPU threads, and so on and so forth. So our implementation goals is, well, one, to create a biologically plausible, scalable architecture for path planning prototyping. FPGAs are great for prototyping, and unfortunately there's just no open source implementations of this available. So people who want to mess around with this architecture right now, you can't, or you write a software implementation which just isn't as representative as what you would be doing in the field on a drone using real neural algorithms that model the way your brain works. And we'd like to utilize things like axonal delay instead of using your traditional multiplicative weights, because it leads the way to a sort of temporally sparse encoding, which allows you to have huge power saving gains, because you only do computation when you spike, and if you spike less frequently and encode the data in that frequency, then you do less computation, which is good because you consume less power. And we'd like to make this very testable. We'd like to make it extensible so that other people can integrate their hardware and reproduce a lot of the results of studies like Jeffrey Kretschmar, he's a researcher from University of Irvine, and he's published a number of papers in this field. So current architecture, sort of a 2D array where each neuron represents a unit of space. We sort of wash parameters across the grid from the control all the way to the end, and once the parameters have been initialized, you can sort of start your simulation, watch your waves propagate, learn delays online in real time. And doing this, we use the neuron manager, which is a concept that I came up with, which sort of allows you to make efficient usage of the hardware that exists on the FPGA. So in the interest of time, thank you for listening, and I'd like to thank my advisor, Dr. Anoop Das, who sort of inspired me to even get into neural networks to begin with, the Astronaut Scholarship Foundation for flying us out here and letting me meet all of you wonderful scholars, and Drexel University for this being the first year that we're part of the Astronaut Scholarship, and I'm super happy to be here.
Great, thank you so much. Who has a question for Thomas?
I actually have a question. So I'm curious, because different neuronal populations have different spike patterns and also propagation speeds, do you have like a specific type of neuron or like a neuronal population that you base this data off of? Or do you kind of generalize everything, average it, and then use that?
Yeah, that's a great question. So neuron models are very complicated, and your brain does a lot of really complicated stuff. There's a really advanced neuron model called the Hodgkin-Huxley model, which has like 1 billion parameters and you use really complicated, oh, you're a neuroscientist, you know all of this. Yeah, so it was on a slide, and I didn't say it specifically, but it's the leaky integrate and fire neuron, which is like the simplest you can imagine, which is great because when you only have so much hardware on your FPGA and you literally can't just add more RAM to your system, you need to be able to tile it and have as many neurons as possible. So it's extremely simple. You just add a bunch of numbers together, and once you get to a threshold, you go back down to 0. And our axon model is even simpler. When you want to spike, instead of immediately propagating that spike, it just goes into a delay where you have a counter, you hit 0, the spike propagates. So very simple stuff.
Thank you. One more question. Who has one?
Okay, so for the non-computer scientists in the room,
yes,
what can you do with this?
Yeah. I mentioned it at a couple points, and I think I didn't make it clear enough sort of what the really cool applications of this are, which is right now, especially ground-based drones. Air-based drones are sort of, it's almost a little bit easier to do pathfinding because you don't have to worry about like traversing on ground, which can have like variable like speeds. Like if you're traveling through like a marsh or sand or like asphalt, you know, it's like easier or harder to travel on that. And so this sort of thing can learn those dynamic environments totally like on the fly. You don't have to give it anything to start with, just, you know, initialize every parameter to 1 and start from there. And this can allow you to do things, and the word, you know, dynamic environment doesn't really say anything. So for example, like disaster relief, right? Like that could be changing all the time. A building could fall over while your drone is moving, and the drone needs to be able to plan around that without having to relearn the entire environment. So sort of in the way that if I tell you to go from here to the other ballroom, but I tell you that that door is closed, you might go that way. And you don't have to walk around and look at everything to reconstruct that map. You can just sort of see it. That's what this algorithm implements and what it would allow you to do for ground-based drones in those sort of dynamic environments.
Great. Love to hear the application. Thank you so much. Well, we've come to the final presenter. Dun, dun, dun. And it's Arjun Gupta, and he's going to talk about Rebel. What a way to close.
All right. Hi, everyone. Thank you so much for being here. It's an honor. And thank you for the great introduction. My name is Arjun Gupta, and I'm a senior at Purdue University studying computer engineering. And today, I'm really excited to be here to share with all of you my research, which is all about large language models for task allocation in human-robot teams. And I'll get into a little bit more detail about what REBEL actually stands for, so just stay tuned for that. So let's kick things off by talking about AI. Now, we are really living in an incredibly unique time with what is going on in the world with AI. And honestly, right now, we're living in the era of agentic AI. We have models like ChatGPT, Gemini, Claude, all these things, but since they were released, nowadays, they're not just doing one-shot question and answer. What they're able to do is they're able to function as real agents. They're able to search things on the web, access tools, do their own reasoning, consolidate all this information before finally giving us the answer. So we are in the era of AI agents. But where is AI going in the future? The next big wave of AI will likely be physical AI. And physical AI refers to AI models that are able to not just understand the internet, but able to understand the physical world around us, understand 3D physics, geometry, kinematics, dynamics. And the way that that manifests itself in the real world is through robots. Now, robots and physical AI is great, but to me, that's just step N. What I'm really interested in is step N+1, and that is when we have robots working together with humans. And that is this whole concept of human-robot teaming. Now, human-robot teaming is great, but let's scale that up. Let's think big. And by that, I mean multi-human, multi-robot collaboration. This is where we have large-scale teams of multiple humans working together with multiple robots to accomplish things that neither one of these things could do by themselves. And here are just some example industries where there's a lot of potential value add. Now, a critical step in human-robot teaming is what we call task allocation. This is where we try to figure out how to best allocate tasks within the mission to humans and robots. And we're not only concerned about generic task allocation. What we're really interested in is preference-aware task allocation. This means, given a specific mission context, how do we do task allocation such that we satisfy and accommodate particular user preferences? So to make this very real, let's think about some real-world applications. And since we're here all as astronaut scholars, let's think about space. Now, colonizing the moon and bringing humans to the moon, been there, done that. Okay, let's think even bigger. Let's bring ourselves to Mars. So think about a human colony on Mars. We've got humans and robots working together, and we want to do data collection. In a normal data collection mission, some of your top preferences might be to maximize the data collection quality or to maintain balanced workload across all the agents. But this changes. Your preference when there's an incoming dust storm may be to, first of all, do the data collection as fast as possible, and then also minimize human exposure. So it's very clear that task allocation needs to be done in a way where it's preference-aware based on the particular context. And this is the particular need and gap that we are trying to address. So our approach to addressing this challenge is to use generative AI, and we're bringing generative AI to this problem space for the first time. And we propose a new method called REBEL, or Rule-Based and Experience-Enhanced Learning with LLMs. This is a high-level overview of what REBEL looks like, but I'm not going to get into the gory details. I just want to keep it at a high level for now. There are three main stages. The first two stages are knowledge acquisition. This is where we help the LLM gain some additional context before doing its actual task allocation. In stage one, we do rule generation. This is where we have the LLM generate a set of helpful rules or guidelines to follow when it's doing task allocation for a given preference. In stage two, in experience generation, we have it simulate a bunch of random missions, gather some task allocation performance data, and store it for future use. And then in inferencing, we have now the new task allocation mission, in addition to some user preferences. And we develop some new retrieval modules that are able to retrieve the most relevant rules and experience data from before to enhance its decision making. So to evaluate this, we built up a simulation, and our simulation consisted of evaluating task allocation in a real-world case where we are evaluating pollution leakage levels from factories. So the goal here is to have humans and robots visit these factories, take pictures of them, and figure out whether they're hazardous or not. So we collected a lot of results. We did a lot of experiments. I want to focus on one key one over here. And this is where we had task allocation given multiple preferences simultaneously provided to the LLM, or to our system called REBEL. So here we see a few different graphs. In each graph, you see three missions. Each colored line of mission indicates a mission where one particular user preference was the priority, as you can see with the labels. And also, for each mission, we evaluate a few key metrics. So task performance, mission time, and human workload. And what we can see is that REBEL, the graph on the right over here, is the only one where the metric that achieved the highest score in the mission was the one that was actually the one we told REBEL to prioritize. And that's indicated by the blue, yellow, and green dots at the very top. So this shows that REBEL is able to understand and accommodate multiple user preferences simultaneously and do that better than some of the leading state-of-the-art approaches. So that's where this whole field is at right now. That's where task allocation is at. But let's zoom out and again think about the bigger picture. Where is human-robot teaming headed? In the future, there are a couple of key promising directions. The first is bringing foundation models that can better understand the physical world and ones that can better understand human preferences. And this comes through building better and bigger GPT-like models. The next thing is what is called building a data flywheel to learn human preferences. So as we have robots work with humans, we want to use that additional data that is learned every time to enhance the robot's ability for future missions. So in effectiveness, we are building this continuous flywheel that allows for continued learning. And then finally, safety and trust is an absolute priority, and that is another area in which there's tremendous opportunity for research here. All right, so with that, before I close, I just want to give a massive thank you to my primary advisor, Dr. Min at the Smart Lab, and all the other Smart Lab folks that were involved with this project. And then also a huge thank you to the Astronaut Scholarship Foundation for organizing such a fantastic set of events this week and for giving us all the opportunity to be here and to present our work. It's been absolutely amazing getting to know you all. So thank you all, and I'd be happy to answer any questions.
Thank you, Arjun. Thank you, thank you. Who has a question for Arjun?
What degree of user domain knowledge is required for setting those initial goals?
Yeah, that's a great question. And those initial goals, like you mean the preferences, yes, yeah. Right? Yeah, so the preferences would be set by, you can think of it as a mission commander. So whatever mission is the one you want to do task allocation for, the primary commander or chief of that is going to be setting those preferences. So in terms of what level of domain knowledge is required, it's whatever the commander has, and that's why it's well suited, right? The person with the most knowledge is going to be setting out these preferences in the first place.
One more question for Arjun.
Hi, fantastic talk. Thank you so much. I am like...
Okay, there you are.
Oh. Sorry. I'm here. Hi. Hello. Okay. I know nothing about this. This is the opposite of what I do, so this is very naive. And this is also about preferences. When you talk about setting for human preferences, I mean, humanity, we're like the most diverse thing ever. Like, we all have large scale, right? If you have these robots doing these things and they're operating on human preferences, like how do you account for the diversity in these types of models going forward? Sorry, that's a big question.
No, it's an absolutely important question and something that is huge in research right now. I mean, there's a whole domain of research called preference learning, and they're using techniques like reinforcement learning from human feedback to integrate some human input into the learning process to help these models learn about these preferences. And the other thing is just building new models that are trained on even more data that have seen what human preferences are and how they can play out in the real world. And just going back real quick, that second bullet point, building foundation models that can adapt to human preferences, I mean, that's exactly what this is. So this is a huge research area, and it's a major focus.
Thank you. This is epic and terrifying.
Thank you so much, Arjun.
Thank you.
And we close the conference with the phrase epic and terrifying. So fantastic. That was our last presenter for the third session of the technical conference. So I just want to say a brief thank you to all the distinguished guests, family, ASF alumni, PIs, support system that helped make this group of people absolutely outstanding. Thank you all.